Good morning, Tornada. Morning. Kindly tell me audio, video, and screen. Is it okay? Audio, video, and screen. Right. So we'll start the session. So this is a other part of power system, that is transmission and distribution. It's a part of power system only. So these are my details, what I have given you earlier also. Yeah. Right. So let's see what are the various topics to be discussed. Okay. Yeah. So in this transmission and distribution series. So these are 8 topics what we have in our syllabus. Maybe gate. I'm saying this only in the view of the gate examination. Okay. In case of IES examination, some more topics will be added to this. Okay. So let me read all these topics what I have given here. Yeah, see this first one, basic concepts of power transmission lines. First topic is basic concepts of power transmission lines. So in this basic concepts of power transmission lines, what we concentrate is mainly types of conductors. What are the different types of conductors? And more introduction with respect to the transmission line, classification of transmission, voltage levels, all these things we are going to discuss in the first topic, that is basic concepts of power transmission lines. Okay. Yeah. Second topic, that is a transmission line constants calculation. In this, we will be concentrating in the calculation of resistance, inductance, and capacitance of transmission lines, single phase lines as well as for the 3-phase transmission lines. See, while we are moving on to this calculation of inductance and capacitances, we will be discussing about the geometric mean radius definition, geometric mean distance definition, GMR and GMD concepts also we are going to discuss in this. Okay, next one. Steady state performance analysis of lines. Steady state performance analysis of transmission lines. See, in the steady state performance analysis, we are going to discuss about types of transmission lines. What are the different types of transmission lines we'll discuss? Types of lines we'll discuss. And we will be moving to ABCD parameters of transmission lines. ABCD parameters, and particularly we will put our concentration. Particularly, we will put our concentration mainly on the long transmission line, and lossless long line, as well as surge impedance loading. Long transmission line, and then we will be putting our concentration on surge impedance, loading, power transfer equations, as well as we have one more topic like power equations. All these things will come in the category of the steady state performance analysis of the transmission lines, which is very, very important. This topic is very, very important in the view of the gate examination. Yeah. Fourth one, transient analysis or wave traveling phenomena. We used to get questions in this area of wave traveling or transient analysis long back in the gate. Maybe in 2010 we had one question. And after that we didn't find any question in the transient analysis and wave traveling. But still as a topic, not only for GATE, for remaining aspects of your examinations also, it is required. Okay, so we'll be thinking this transient analysis in the way of the problematic orientation mainly. Okay, yeah. Next one is voltage control and power factor correction. It is also one of the very important area from where we will be getting the questions in the GATE examination. Particularly, I can say power factor correction. Okay, to improve the power factor, what is the rating of compensation to be added? Or if you remove the compensation, what will happen to the power factor? And voltage control, shunt reactor bank rating, shunt capacitor bank rating, such type of problems we used to get in the GATE examination. Okay, yeah. Next one will be underground cables. Our view in the underground cables only in the problematic orientation mainly. Just few formulae we have. We will be collecting those formulae and we will be solving some problems on those formulae. Okay, just capacitance calculation of cable, insulation resistance calculation of cable. These things we are going to discuss. Next one is overhead line insulators. Particularly, we discuss about the string efficiency of overhead line insulator and how to improve the string efficiency. This is an important topic in the overhead line insulators. String efficiency and improving the string efficiency. Next one will be distribution systems, and we will be discussing what are the different types of distribution systems and what are the advantages and what are the disadvantages and some problems in the distribution systems. These are the various topics what we are going to take up. And as I said you earlier, particularly in the view of the GATE examination, most important things in this whole will be the third chapter, steady state performance analysis, and the fifth chapter, that is voltage control and power factor correction. And second one also a bit important only, just they will ask to calculate the inductance and capacitance values. Just they will ask to calculate the inductance and capacitance values, and just by using formula you can get it after calculating the values of GMR and the GMT. Okay, yeah. So regarding the weightage in the examination, I am saying this is only with respect to the GATE examination. I am saying this is only with respect to GATE. As far as ESE is concerned, we have some topics like HVDC, tax devices, distributed generation, as well as smart grid. Okay, these topics will be discussed for the ESE people separately for the prelims examination. Okay, yeah, let's continue. See, weightage of this topic. See, particularly we discussed this one, but still I am writing that GATE examination. If you talk GATE examination, total power system will give around 10 to 12 marks. 10 to 12 marks. And whereas if you think about only T&D part, so in the 10 to 12, we used to get around 4 marks. Sometimes 4, sometimes 5, even sometimes 3 also. Even they are giving for 3 marks, they will give a qualitative question. They will give some qualitative questions in the examination. Very conceptual questions they used to give in the T&D, particularly in the third chapter, so-called the steady state analysis. Okay, yeah. Next. So as far as ESE is concerned, we used to get around 5 questions in T&D. I am saying 5 questions in T&D. Okay, so in that whole 15 to 20 questions, we used to get 5 questions from the T&D. Yeah. And moreover, they are going for some untapped areas, both in the ESE as well as in the GATE examination. And we will be discussing about those areas, and we will be highlighting those untapped areas also while we are moving on to the discussions. Yeah, next thing. So regarding textbooks for reference, just go through these textbooks. I think in the earlier class also, maybe in the F&S also, I have given these textbook names to you. Okay, only for reference, I am saying you these things. First one is Power System Analysis and Design by Duncan Glover, sir. Okay. Second one is a Power System Analysis by Stevenson, sir, and Granger. And there is one book which is specifically written by Stevenson, sir. specifically written by Stevenson sir, that is Elements of Power System Analysis. Elements of Power System Analysis by Stevenson sir. Okay, and the next one is Electrical Power Systems. Electrical Power Systems. This is by Professor Hawari. This is by Professor Hawari. And next one is a Power System Engineering by Nagaratan Kothari. Nagaratan Kothari sir. Okay, and other than these things, we can find many textbooks in the market like Power System, Electrical Power Systems by C.L. Wadhwa, or Electrical Power by J.B. Gupta. Like that, you can find many textbooks. But what I suggest, particularly for TND, with respect to GATE examination, is try to practice the notes as many times as possible, because any faculty, whoever is teaching here, might be amalgamated all the textbooks together, as well as a previous GATE as well as IES experience. Okay, so that they are going to furnish in their notes, such that the student should not go for any other source to take up some more what we call analysis, such that the notes is going to be set up, as well as the teaching is going to be set up by any faculty whoever is teaching here. Okay, so in my view, what I suggest is you practice the notes thoroughly as many times as possible, as well as you go through the previous GATE questions and IES questions. Try to analyze them. Try to analyze those questions as much as possible. That will give a good experience to you to write the GATE examination. Okay, yeah. So anyhow, if anybody asks me which book you suggest is, I will be going with all here. Particularly Stevenson, I will think in some part of Power System Analysis. Hawari, I will think in some part of TND as well as analysis, and the Power System Analysis and Design, also a good book, right? I can't judge which book is a good one among these things, but if you want to practice the problems, you can go for what they call Power System Engineering by Kothari, if you want to solve some problems, because as it's an Indian author textbook, it might be in our Indian orientation, right? Okay, fine. So let's move. The first topic or first chapter what I have given, that is basic concepts of power transmission. That's what the first one I have given, right? Basic concepts of power transmission lines, or you can say basic concepts of power transmission. Yeah, next. Listen. Look, what do you mean by a transmission line basically? What is the meaning of the transmission line basically? Tell me please. What's the definition of transmission line? Generally, we can say, yeah, in a simple word, what I can say is transmission line, it's a power conductor or electrical conductor which is used to transfer the power or electrical energy from one place to other place. Okay, else we can say simply transmission line, it's a link between the generating station to the load center, or a link between two buses in the system for the electrical energy transfer. Yeah. So I'm writing that small definition here. Transmission line. It's a link between generating station and load center. Or as we said earlier, it's simply a link between two buses in the system. Or you can call this one as a link between two buses in the system. A link between two buses in the system. Yeah. Next thing. What material we are going to use for this line? what material we are going to use for this transmission line. See, definitely it's a electrical conductor. There is no doubt about it. It should have a good conductivity to transfer the electrical energy. Okay, so I can say it's an electrical conductor. Basically, the transmission line is an electrical conductor. Electrical conductor. Okay, so it's an electrical conductor. Yeah, tell me now. Tell me please. What are the materials which is having good conductivity? What are the materials which are having good conductivity? I will give some examples to you. I will give some examples to you. Yeah, could you please tell me? Could you please tell me which material is having highest conductivity? Which material is having highest conductivity? Tell me please. Silver. Silver. Silver will have the highest conductivity. Silver. Silver will have the highest conductivity. Ag, silver. After silver, we have copper, and then we have aluminum, and then we have iron, gold. These are various examples for the electrical conductors. What my view here is, silver is having highest conductivity among all these things. Remaining also conductors only with less conductivity compared to silver material. Okay, silver, copper, aluminum, gold. Okay, listen, please. Not only these four, we have many materials. I have written only four on the board. That's it. Yeah, tell me now. Tell me. Among these four, what I suggested, which material we are going to prefer? That question we have to ask ourselves. We have many conducting materials. Okay, which material we have to suggest for the line manufacturing? See, silver and gold are very high cost, precious metals, right? Silver and gold are of very high cost. These are precious metals. We can't go for these two. Precious means costly. Okay, very less available metals. So we can't use these two. And we have to go for these two now. Copper or aluminum. Copper or aluminum. Which one is suggestible among these two for transmission line and distribution line? I'm talking. Transmission line and distribution line. That is mostly aluminum. Right. So I can say aluminum. This is used for transmission and distribution lines. Used for transmission and distribution lines. Transmission and distribution lines. Where we use copper? Anybody? Anybody? Can you tell me, please? Can you please tell me where we'll use copper? Copper. In the house wiring. In the house wiring, we'll be using copper conductor. House wiring as well as machines, small rating machines. Small rating machines as well as small rating transformer windings. Small rating transformer windings. For these things also, you'll be using copper. Yeah. So for house wiring, we'll use it, as well as small rating machine side. Small rating machines. We'll be using the copper material. Okay. Tell me, in the view of what we call transmission and distribution lines, why you are preferring to go with aluminum? That's the question. Okay. Let me write in the next slide. Yeah, if you have not completed the slide, you can ask me. You can ask me in that what we call in the comment session. I will be reading the comment session every time, but somebody has told that Sari is not seeing it. Okay, I will be looking at Q&A regularly. Yeah. So class is up to 9:30 Class is up to 9:30. Yeah, let me write in the next slide. Aluminum is preferable for the transmission line manufacturing. Aluminum is preferable for line manufacturing. Transmission line manufacturing. Okay? Yeah. What is the reason to choose aluminum? Somebody is saying abundantly available. That's okay. Abundantly available. And I say economical. Cost of aluminum is less compared to copper. I am saying with respect to copper. Okay. So low cost compared to copper. Okay. If you want, just you go through the newspaper and you will find a stock market list in that commodities value something they will give. There you can find what's the aluminum rate per kg, copper rate per kg. Like that you can observe. Maybe aluminum rate per kg may be 120 rupees, whereas copper might be around 200. So in that view, aluminum material cost will be low compared to copper cost. This one. Next one is density. Density of aluminum conductor is less compared to copper. Density means what? Density in the sense simply weight per volume. Weight per volume. So same volume material you have taken. Same volume aluminum and copper conductor you have taken. Aluminum conductor weight will be less for that volume compared to copper. That's the thing what I am saying. Sometimes the people will say less weight also. Okay. So both statement I will write. Both statements. So I can say less density. Less density. So you can write it's in kilogram per meter cube, or you can call less weight also. Less weight. Okay, like that you can say less weight. Next thing. So does rich countries use silver for T&D? No, Satvik. No. Next thing. To say about the next advantage here, I will be discussing one small topic here. Just look here. To write the third one, before writing the third one, a small basic topic I am going to discuss. Just listen, just listen. See, what is the resistance formula for a conductor? What is the resistance formula for a conductor? I will show the conductor to you. For example, I have a conductor something like this, having some length. Okay, so this is one conductor we have, made by any material, doesn't matter. So it is carrying current in this direction, let's say I. Length of the conductor is L, and this conductor is made by a material rho, resistivity rho. Material is made by a resistivity rho. Okay, what is the resistance of this wire? That is simply rho L by A. Very simple question. Resistance of that particular conductor is rho L by A. Rho L by A. Yeah, rho L by A. I am asking you one simple question to you. What will be each and every number here? What will be that each and every number? What is rho? I said resistivity of material. Resistivity of material. What is L? Anybody please tell me what's L here? In the resistance, what is L? What is L? Length of? Yeah. Listen please. It is not length of conductor, strictly speaking. It's not length of conductor, strictly speaking. If anybody asks you this type of question in any interview or examination, what you should say is length of current flow. In how much length the current is passing, that length we should take for the resistance. What is the basic meaning of resistance here? What's the basic meaning of resistance? It's a property of material which shows opposition for the current flow. Yes or no? Property of material which shows the opposition for the current flow. Means whichever the path through which current is passing, that path only we should consider to calculate the resistance also. Yes or no? So L is the length of current flow what we have to consider. L is the length of current flow. Length of current flow. What do you mean by A here? What do you mean by A? A is a area of cross section. That's okay. Area of cross section of conductor. You are saying me area of cross section of conductor. That's okay. But I will ask one very simple question. Very simple question. Just listen to me. For example, just look here. For example, this is one conducting body I have. Let me assume that we have one conducting body something like this. This is one conducting body. Okay. Now I am sending some current. In this direction. Into this conducting body, we are sending some current in this direction. What is the area A we have to consider now? What is the area A we have to consider? This area we have to take. This rectangular area we have to consider in the denominator. Yes or no? Because current is flowing in this particular direction. Same conductor, current is flowing in this direction, let us see. Current is flowing in this particular direction. What area we have to consider now? Is it the same area of previous or different area? What area we have to consider? Is it same area or different area? Definitely it's a different area. Different area. Different area means this area we have to consider now. And what is that area means? Area measured perpendicular to the direction of the current flow. Area measured perpendicular to the direction of the current flow. That we have to consider in the denominator. This point should be very, very clear while you are calculating the resistance of a conductor. So I think all of you getting this point what I discussed. Is it okay? Is it okay for all? Please kindly tell me. Yeah. So this A is a area measured perpendicular to the current flow direction. Current flow direction. Okay, now see if it's a circular conductor, area measured perpendicular to the direction of the current flow means obviously it will be circular cross-section area. So I use it to write many times as pi r square if it's a circular shape of conductor. Okay, done. Next thing. One very simple question from this formula. One very simple question to you. If for constant resistance, I'm writing like this. For constant resistance value, R value, if resistivity was increased, look here, for constant resistance value, if resistivity value was increased, what should happen to area of cross section? What should happen to area of cross section? Kindly tell me. Tell me please. What should happen to area of cross section? Should increase. Very simple thing. See, if resistivity is increasing, area of cross section should increase. Then only this ratio will be constant, right? Because we want to make the resistance as constant, right? So if rho is increasing, area of cross section should also increase. Then only this ratio is going to be maintained as constant. So I can say area of cross section should also increase. That's if rho is increasing, area of cross section should also increase. Yeah. Next thing. Now tell me. I want to compare these two things now because aluminum and copper, that's a comparison we are making, right? For that only we are discussing all these things, aluminum and copper. Among these two, aluminum and copper, which material is having more resistivity? Among aluminum and copper, which material is having more resistivity? Definitely aluminum. Definitely aluminum will have more resistivity compared to copper. Material resistivity will be constant. Shiva, we are comparing different materials, no? We are comparing different materials. Okay. So as aluminum conductor resistivity was greater compared to the copper conductor resistivity. Now, simple question to you again, simple question. If I am manufacturing one aluminum conductor and one copper conductor, one aluminum and one copper, which conductor size looks to be bigger? Which conductor size looks to be bigger? Is it aluminum or copper? Definitely aluminum only, because aluminum conductor resistivity is more compared to copper. So definitely for same resistance value, I can say area of cross section of aluminum conductor will be greater compared to area of cross section of copper. So for example, if I show those two conductors to you, this may be the conductor of aluminum and this may be the conductor copper. Like this you can experience. So aluminum conductor and it's a copper conductor, and the aluminum conductor radius is very, very large, whereas copper conductor radius will be less compared to aluminum. So I think all of you getting this one. All of you getting this? Yeah, good. Yeah, now, listen. Now, I will be applying some voltage for aluminum conductor as well as some for copper conductor. Same voltage. Look here. Applying some voltage V to the aluminum conductor. Applying some voltage V to the copper conductor. Same voltage we have applied. And on this V, we are going to make some more comparison. Okay. I will give conclusion. Just look at the thing, the way how I am discussing here. Look here. I'm moving to next slide. I'm moving to next slide. I'll come back to this one. I'll come back to this one. I'm moving to next slide. Look here, for example, this is one line charge. This one line charge. Line charge. I don't want to confuse you by discussing deep electromagnetic theory concepts. How can we justify which material have high resistivity? That is from table only, Kavita. That is from the what we call periodic table. We are considering which is having high resistivity, which is having low resistivity. Okay, we are not the persons who are deciding it, which is having high and low resistivity. That's already what we call decided. Okay. Yeah. Let's continue. Listen, it's a line charge. Line charge. I'll say line charge. It is denoted like plus q coulomb by meter. Plus q coulomb by meter. Now, I'm staying at some point x beside the line charge. Beside the line charge, at some point x I am staying. This point is at a distance of x from the line charge again. That point is again from a distance of x from the line charge. Yeah. Tell me now. Tell me. What is the electric field intensity at this point x? That's the question. What is the electric field intensity at this point x? Okay. So if you have learned electromagnetic theory, it is well and good. Even though you have not learned it, just listen from this one. That whatever the formula I am saying you, that is sufficient for our discussion. Okay. Fine. See, from this line charge, at some point x, the field intensity formula for the field intensity will be Q, charge value Q, by 2 pi epsilon into distance. How much is the distance value? X you have to keep. Okay, Q, charge value, by 2 pi epsilon into X is a distance. That is the electric field intensity at some point X beside a line charge. Clear? Now, next thing. For example, if you take up the conductor size, something like this. I'm showing the conductor size. So these are the outer sides of the conductor. Just go through these things. It's a conductor, I'm sure. It's a conductor, and this conductor is having some radius of r. This conductor is having a radius of r, I can say. R. Now, listen. Simple. If I am moving this point x onto the conductor surface, if I am moving this point x onto the conductor surface, then definitely we will get field intensity on the conductor surface. Definitely, we will get the field intensity on the conductor surface. Yes or no? Tell me, all of you. Krishna Priya, resistivity is a constant number. It won't change, even though you change the dimensions. Resistivity is defined for the material. Look here. Resistivity is defined for the material. Resistance is defined for an object. For example, if this is one material I have, this material will have some resistivity, and this conductor, or you can say this body will have some resistance. That resistance depends upon resistivity of this material and dimensions of this body. Okay. Yeah, let's continue. Simply in place of x, we are going to keep small r. Okay. So field intensity on the conductor surface is small r is nothing but q by 2 pi epsilon into small r, you can say. Okay. From this, one simple conclusion what you can write is field intensity on the conductor surface is inversely proportional to radius of the conductor. Field intensity will be inversely proportional to radius of the conductor. Okay. Actually, you can ask me in the doubt session that doubt what you have. Okay. So field intensity is inversely proportional to radius of the conductor. Now, let me move back to the previous slide. Move back to the previous slide. Tell me now, after applying same voltage for both conductors, aluminum and copper, on what conductor surface field intensity will be less? This is the field intensity on the aluminum conductor, and this is the field intensity on the copper conductor. On what conductor surface electric field intensity will be less? Tell me please. Yeah, definitely on the aluminum because of its larger size. Larger size. Okay, let me write that comment now. For same resistance value as radius of aluminum conductor is greater compared to radius of the copper conductor. But you know, electric field intensity is inversely proportional to radius. So definitely what I can say is electric field intensity on the aluminum conductor will be less compared to electric field intensity on the copper conductor. Electric field intensity on the aluminum conductor will be less compared to electric field intensity on the copper conductor. Then you please tell me, what is the problem of this electric field intensity now? What is the problem? Why you are thinking about this electric field intensity? What's the problem of this? Particularly, if that electric field intensity on the conductor surface, it becomes higher than the dielectric strength of surrounding dielectric medium. Dielectric strength of the surrounding dielectric medium. Then definitely there is a possibility of breakdown of the dielectric material on the conductor surface. That we are going to call many times as corona. So if the field intensity is more on the conductor surface, possibility of getting corona will be more for that particular conductor. Okay, so let me write it. So I can say, as electric field intensity on the aluminum conductor is less compared to copper, I can say corona possibility will be less for aluminum conductor compared to copper conductor. Corona possibility will be less compared to aluminum conductor, for aluminum conductor compared to copper conductor. Okay, so as time comes, just I will define what is corona, and I will be discussing about this corona again and again in the bundle conductors after maybe in the next chapters. Okay, so first I am going to define only corona here. Okay, don't get a doubt about it. Just listen that point, what I'm saying. I will be explaining about this corona in the bundle conductors. Whereas for IES people, ESC people, the corona will be discussed as a special topic also. Okay, yeah, corona. Simple. If electric field intensity on the conductor surface, electric field intensity on the conductor surface greater than, look here please. Corona will be less in aluminum, right? Hemalata, already we have discussed that. Electric field intensity is less compared to, inversely proportional to radius. Yeah, larger area is an advantage only, right? That's what we are discussing now. See, look here. Let me conclude the thing. Just look. First, what you have taken? Definition of line. Then, which material we have to take? I have said I have given 4 materials. Among the four, aluminum and copper we are discussing now. And among these two, again, aluminum is suggested compared to copper. What's the reason means? One reason you said low cost. Next reason you said less weight. Okay. Now the third reason what we are saying is aluminum conductor looks in bigger size compared to copper. Aluminum conductor looks in bigger size compared to copper for same resistance value. For same resistance value. In that perspective, electric field intensity on the aluminum conductor will be less compared to copper conductor. So corona possibility will be less for aluminum conductor. It is one of the good advantage of aluminum compared to copper. It is one of the good advantage of aluminum compared to copper. Yes or no? This is one of the reason why we prefer aluminum conductor for transmission lines as compared to copper. All of you getting my point? Yeah. Yeah, good. Let me continue. Electric field intensity on the conductor surface greater than dielectric strength of surrounding dielectric medium. Mostly that surrounding medium will be air. Okay, I'll write a letter G. G is dielectric strength of air. Dielectric strength of air. Then there is an ionization. There is an ionization on conductor surface. On the conductor surface. There is an ionization on the conductor surface. It is known as corona. It is known as corona in the transmission line wires. It is known as corona in the transmission line wires. Okay. Yeah. Fine. What is the G? Dielectric strength of air? How much? Anybody? Can you tell me? What is the dielectric strength of air? Dielectric strength of air. Dielectric strength of air. Ionization means it's a breakdown simply. Ionization means it's a breakdown on the surface of the conductor. See, actually, this value, dielectric strength of air will be 30 kV per centimeter. 30 kV per centimeter is a dielectric strength of air. Dielectric strength units will be kilovolt per centimeter. Dielectric strength units will be kilovolt per centimeter. Electric field intensity also in the same units, kV per centimeter only. Electric field intensity also in the same units of kilovolts per centimeter. Okay, dielectric strength also in the same units of kilovolt per centimeter. 30. But particularly, many times we'll be dealing with sinusoidal voltages. So no, maybe AC transmission lines we are discussing. So in that view, we are tackling with sinusoidal voltages. If you are going for that sinusoidal voltages, this G value the people will take as 30 by root 2 kilovolt per centimeter RMS. 30 by root 2 kilovolt per centimeter RMS. Like that also the people will write. And this the people will say as a peak value. So I am saying G is equals to 30 by root 2 means it is the value 21.21 kilovolt per centimeter RMS. Let me give clarity. This one is valid only for sinusoidal signals. This one is valid only for sine waves or sinusoidal signals or voltages. Whereas the 30 kV per centimeter is valid in all cases. Okay, it may be a DC signal, impulse signal, sinusoidal. For any case, this number will be valid. If it's a sinusoidal, listen please. If it's a sinusoidal, you might be getting a doubt. Sorry, you said 30 one time and 21.21 one time. Which value we have to use? At that time, you take the 30 as a peak value. At that sinusoidal signal discussion, you take the 30 as a peak value, 21.21 as a RMS value. For any other signal you are discussing, DC, impulse, any other signal, you take it as 30, no issue. Okay, so it is valid for any signal. You write in bracket peak, valid for any signal, valid for all cases, all types of voltages, Clear? So from this point, you should not get a doubt about this dielectric strength of air. I've explained you both numbers and which value has to be used at what place. Yeah, next, let's continue. Till now, we have gone with only selection of material for the line manufacturing. Aluminum we have decided finally. Next thing we are going to discuss about what are the desirable characteristics of transmission line wire? What are the properties required for the transmission line wire? Okay, yeah. So let me take next slide. Desirable characteristics of transmission line. Desirable characteristics of transmission line. Okay. So maybe I'm discussing this only in the designing stage here. I'm discussing this topic only at the designing stage. Okay. Listen, stop writing. Just listen to the words, what I'm saying first. I'll give some time to write. See, the basic definition of transmission line, already we said, it's a connecting link between a generating station to the load center. So we have a generator and we have a load here. Load, and this was a generator. Okay, fine. Listen, it's a line. Very simple question. For example, my load is demanding a power. Load is demanding a power of 30 megawatt. Load is demanding a power of 30 megawatt. How much power the generator has to generate? How much power the generator has to generate? Is it 30 megawatt or more than 30 or less than 30? Tell me all of you. Is it more than 30 or less than 30 or equal to 30? Definitely more than 30. Why? Why it has to supply more than 30 means we have some losses in the transmission line wire. So we have some power loss in the transmission line wire. So this generator should supply a power more than 30 megawatt in order to meet the power loss as well as a load demand. So is it a desirable thing to supply the power loss to the transmission line? No. See, actually, our line, whatever we are thinking here, listen please. Our line, whatever we are thinking here, should not consume any electrical energy. Our line should not consume any electrical energy. That is one of the desirable characteristics of the transmission line. Else, it is not possible to make that loss as zero. It is not possible to make that loss as zero. At least we attempt to maintain that loss value as low as possible. Okay, that is the first property required. So first desirable characteristics of transmission line is power loss in the line. The line must be as low as possible. As low as possible. Should be very, very low. Minimum power loss we have to maintain. Okay, second one. It's also very simple. Just listen. Stop writing, please. Stop writing. Just listen to me. See, at the receiving end side of transmission line, receiving end side we will call this, and this we will call as sending end. Okay. At this receiving end, we have a voltage of mod VR. Sending end side, we have a voltage of mod Vs. Simple thing, very simple thing. Just listen. The receiving end side, we have voltage mod VR. Sending end side, we have a voltage of mod Vs. In a general perspective, How will be the receiving end voltage compared to sending end voltage? How will be the receiving end voltage magnitude compared to sending end? Generally less. Okay, so I'll say the same. Mod VR value will be less compared to mod VS. Receiving end voltage value will be less compared to sending end voltage. Why? Why it is less? Anybody? Why it is less? Anybody tell me please? Why? Why it is less? Because of voltage drop, not because of loss. Salman Khan and Imtiaz, it's not because of power loss. It is due to voltage drop in the transmission. Okay, so we have some voltage drop in the line that is making the receiving end voltage magnitude less compared to sending end voltage magnitude. Okay, done. Next. What's the problem of that low voltage? In that perspective, we have to discuss. What's the problem of that low voltage? Listen. Generally, I will explain in a brief way. Just listen. Generally, load in the sense, what type of load we have? Load in the sense, what type of load we have? Is it okay? Audio, is it okay? Audio. Somebody is saying it's lagging. Okay. Abjit, is it okay, Abjit? Abjit, yeah. Fine. Network is okay. What I'm using now, I think network is okay. Yeah, good. Let's continue. See, mostly we'll be getting a lagging load at the receiving end side. Mostly we'll be getting a lagging load at the receiving end side. Lagging load in the sense, mainly we can find an induction motor. Lagging load in the sense, we can find mainly induction motor, simply like this action. IM, induction motor. See, for example, if the applied voltage to the induction motor is mod V, applied voltage to that induction motor is mod V. Listen. Generally, torque developed by the induction motor, proportional to applied voltage square. Torque developed by the induction motor proportional to applied voltage square. Is it okay? Okay, now tell me, because of the voltage drop in the line, applied voltage to the motor is less. Applied voltage to the induction motor is less, we are saying. If that is less, definitely torque developed by the induction motor is also less. If the torque developed by the induction motor is less, definitely we can say it may not have a capability to meet the load demand. At the time, the motor may comes to stop. So to overcome these issues, right, we have to maintain a good voltage profile at the load location. To maintain To maintain the good voltage drop in the transmission line must be as low as possible. Voltage drop in the transmission line must be as low as possible. Are we getting my point? What I'm saying you? All of you getting my point, please? So I can say the next characteristic of the line required is voltage drop in the line must be as low as possible. Such that a good voltage will be maintained at receiving end side or at the load location, right? At the receiving end. So these are the two desirable characteristics of the transmission line. So voltage drop, it is simply I into Z, you can say. Power loss is a energy loss by form of heat. Hmm? For static load, what happens if voltage, rated voltage? See, power variation will be there. Gopi, power variation will be there. It is a static load if you are not maintaining good voltage at the receiving end side. For example, you take an incandescent lamp, or you can say LED bulb. It may not give a good performance, right? Cannot give a good performance if you are going for low voltage application. Yeah. Next thing we are going to discuss about ratings of transmission line. What are the ratings of transmission line? Yeah, aluminum is not a superconductor. Aluminum is not a superconductor, it's just a conductor. The superconductors are different things. Okay, ratings of transmission lines. Okay. Ratings of transmission lines. See, maybe in the examination, listen please, listen. Maybe in the examination or anywhere, simply if you think about a transmission line, we should think about a three-phase transmission line only. You should not think about single-phase line. You should think about only three-phase transmission line. See, my interest is to discuss now what are the ratings of the three-phase transmission line wires. Transmission lines in the sense three-phase transmission line only we are discussing. Okay, ratings in the sense I will suggest to go for two ratings here. I will suggest to go for two ratings. One is a voltage rating of line. Second one is a power rating. Okay, two ratings I am saying you. First one is voltage rating. Voltage rating of line. Second one is a power. Power is okay. That I am going to call as apparent power rating. Apparent power rating. Second one. Second one is a apparent power rating. Apparent power rating. These are the two things. Voltage rating, apparent power rating. Okay, listen. Generally, see, actually, it is one of the previous gate examination question also. Just I am saying that question, just listen to this. Listen to me. Previous gate exam question. Rated voltage of a three-phase power apparatus. Rated voltage of a three-phase power apparatus represented in the form of per phase RMS, per phase peak, line to line RMS, line to line peak. Which one we have to get? Which one we have to take among the four? Rated voltage of a three-phase power apparatus represented in the form of what? Is it per phase value or line to line value? Next, is it RMS value or peak value? Which one? Which one we have to consider? Line to line RMS value. Line to line RMS value. Okay, so voltage rating of three-phase transmission line will be line to line RMS value. Line to line RMS value. So if you want, I will keep this as simply VLL also you can say. VLI. Line to line RMS value. Next one. See, apparent power for three-phase power apparatus. Three-phase power apparatus, it will be definitely three-phase apparent power rating value. There is no doubt about it. Three-phase apparent power rating. So simply I will say this. Three-phase apparent power rating. Three-phase apparent power rating. Generally, we indicate this with a letter of S. We are indicating this with a letter of S. Yeah. So why not peak? So I'm saying you only standard. For example, if you see outside, for example, we have a generator, right? For example, we have a three-phase generator, let's say, three-phase generator, and it's having a ratings of 13.2 kV, 200 MVA. Okay, so just if you see on the nameplate of generator these numbers 13.2 kV and 200 MVA, immediately what you have to understand is that this 13.2 kV, it's a line to line RMS voltage rating of generator. Okay, and 200 MVA is a three-phase apparent power rating of the generator. That we should think. That's the meaning here. Okay, ratings are represented in that manner according to the flexible usage in the calculations or anything. So it's a line-to-line RMS voltage rating, RMS voltage rating of generator, you can say, and this is three-phase apparent power rating of the generator. Three-phase apparent power rating of generator. Three-phase apparent power rating of the generator. So I think all of you getting this. I will come to that. I will come to that. Apparent. So in electrical equipment, R shows only line to line. Yes. Imtiaz, anywhere, just beside your house, if you have one transformer, beside your house, if you have one transformer, just reach nearby the transformer, try to take the snapshot of that what we call a nameplate, and you observe what is that voltage rating and power rating. If it's a three-phase transformer, they will keep that voltage rating in the line-to-line RMS, and they will keep the power rating in the manner of three-phase. Okay, let me continue. Listen. See, apparent power, and we have some other term like complex power also. Just I will try to give a relationship between them. Apparent power and complex power. Just listen. For example, if you want to know the name like complex power first. Complex power. Yes. Two formula I will give you. Per phase. I'm saying this in the per phase manner. Per phase analysis you can feel. Complex power you can write as P plus JQ. P is a real power. Okay. And Q is a reactive power. P plus JQ. That's a complex power. S is equals to P plus JQ. Yeah. P plus JQ. Next thing. Another formula for complex power I'm not discussing now. I will discuss this in the power equations later. Another formula for complex power, S is equals to V bar into I bar conjugate. V bar into I bar conjugate. That is another formula for the complex power. Same thing. And what do you mean by apparent power now? Anybody please tell me? What do you mean by apparent power? Apparent power is nothing but simply magnitude of this complex power. Magnitude of the complex power is called as apparent power. All of you getting me? Right. So, apparent power is nothing but magnitude of the complex power. So, modulus of S. And modulus of S in the sense you can write it as square root of P square plus Q square. You can write this like E square plus Q square. Else you can write this like in terms of voltage and currents. You can write it as mod V into mod I. S is equals to mod V into mod I. Yeah, good. That's it. This is some small difference you have to identify between the apparent power and the complex power. I will discuss how this is VI conjugate is coming under later. Sir, apparent power is sum of real and reactive power. No, Vijaya Rani Reddy, just go through the thing what I discussed. I will show the derivation later. I said you already VI conjugate derivation. I will show later. Not now. It's not the time to discuss about it. Strictly. Wherever it is required, I will discuss about it. Yeah. Next, listen, please. See, particularly if you think about the three-phase apparent power S here, S is equal to, I'm writing formula. Yeah, listen. This is a notation problem, what I feel. Notation problem. Sometimes we used to call apparent power as modulus of S. Sometimes simply S also. There is no issue with that. S is a letter we will be using sometimes to keep apparent power, sometimes to keep complex power also, along with the name. So I am saying you here apparent power already. Apparent power, yes. apparent power S. Formula for this is root 3 into line to line voltage magnitude multiplied with line current. Root 3 into line to line voltage magnitude multiplied with line current. And moreover, it's a three-phase apparent power formula. Three-phase apparent power formula. Else, the same formula for apparent power S you can write as 3 into phase voltage magnitude multiplied with the phase current magnitude. Like this also you can write. Any formula you can use among these. Okay, apparent power three phase is root 3 line to line voltage into line current. Else you can write 3 into phase voltage magnitude into phase current magnitude. Like that also you can write. Okay, let me continue. Let me continue with this. Can you please tell me what is the current rating of transmission line from this? What is the current rating of the transmission line from this? Current rating of transmission line. Current rating. Just simple formula you can get from this, right? Current rating IL is equals to S three-phase value by root 3 into line to line voltage magnitude. Okay. Current rating. Line current and phase current both will be same in case of transmission line. In case of transmission line current and phase current both will be same. Phase current also same. Yes, three phase by root 3 into line to line voltage. Okay, next thing. Yeah, let me conclude. Till now, whatever we have discussed. Very simple discussion. First, what we have started is definition of line. So after the definition of line, we have gone with the what we call material selection. Okay. So after material selection, then we have moved on to what we call why we are selecting that aluminum material and that we discussed. After that, we have gone with the characteristics of line. Now we are studying about ratings. From this point onwards, what we are going to discuss is what we are going to design the transmission line. How we are going to design the transmission line. Particularly, electrical design of the transmission line we are going to concentrate. Electrical design of transmission. Yeah. Yeah. So from this point onwards, we are going to continue with the topic like electrical design of the transmission line. Design of line. Electrical design of the transmission line. See, in this electrical design of line, we will be concentrating mainly on two things here. One is a conductor size selection. And second one will be obviously, okay, we'll discuss about that, Pranay. Power rating is given in per unit. You asked me that doubt in doubt session, Ankur. I will discuss about that per unit. Already we discussed about it. Yeah, listen please, listen. Two things we are going to discuss now. One is a conductor size selection. Next one is the insulation level calculation. Okay, first one, conductor size. Generally, who is going to decide the conductor size? Transmission line conductor size. Who is going to decide? Current rating. Definitely, it will be decided by the current rating. And what's the relationship between these two? Conductor size and current rating. What's the relationship between these two? Yeah, tell me please. See, whenever you want to send more and more amount of current, obviously we have to increase the size of the path, size of the current flow path. So obviously the area of cross section of conductor, what you are going to choose, it should be depending on the current rating of the conductor. Particularly, I can say RMS current rating of the conductor. Okay, yeah. So let me continue. Directly proportional. So conductor size, conductor area of cross section, area of cross section proportional to current rating of the conductor. Current rating. In bracket, I will say RMS current rating. RMS current rating. Yeah, this one. Second one. Insulation level. Next one is insulation level. You write, if you want here, A proportional to area of cross section proportional to current rating. Area of cross section proportional to current rating. Now, next one, please listen now. Listen now. Insulation level. Generally, in case of overhead lines, we are going to discuss here. Overhead lines, we are going to discuss. Where we will be keeping the insulation in case of overhead lines? Where we will be keeping the insulation in case of overhead lines? In between tower and the power conductor. See, actually, if you just look at the overhead line outside, just listen to me. If you just look at the overhead line outside, you don't have any insulation on the conductor surface. You don't have any insulation on the conductor surface. At the support, so-called at the location of tower, between the tower and the conductor, we used to keep the insulator. Okay, so let me show in a simple diagram. So maybe it's a tower we have. It's a tower. Okay, and it's a power conductor. We have something like this. It's a power conductor, and between these two, we have this what we call insulator, overhead line insulator. Okay, overhead line insulator. So this is a placement of the insulator. You have to see. Okay, based on what criteria we are going to keep this insulator? On what basis we are going to select the insulation level? On what basis we are going to select the insulation level means simply listen, please. Listen to me once. I am saying you this one. Just listen. See, we have connected that insulator between the conductor and tower. Means whatever the voltage you have between the conductor and tower will appear across this overhead line insulator. Whatever the voltage we have between the conductor and tower will be appearing across this overhead line insulator. So we should select that insulation strength based on how much amount of voltage you are going to apply. So simply in this particular point, what I'll say is overhead line insulator strength was selected based on voltage level. Strength was selected based on voltage level. So I think all of you getting this voltage rating, you can say, or voltage level, whatever it is. Okay, so from this point, we'll be continuing. Yeah, I will discuss string insulator later. Maybe a string insulator, what I have drawn here. Yeah. See, I will be taking up this discussion specially now. So selection of insulation level for the overhead line. That's the topic what we are going to discuss further. Okay. So next heading I can say selection of overhead line insulation level. Insulation level. Yeah. Selection of overhead line insulation level. Yeah, so you take a break of 10 minutes, 10 minutes break. Generally, we don't use to give a break in the span of 6:30 to 9:30, but so many of you are asking me. So I will give 10 minutes break at a time of 8 a.m. daily. 8 a.m. At 8 o'clock morning, I will give 10 minutes break daily. Don't ask me in between the class. When you will give break, please give me break. Please don't ask me such type of things. Okay. So 10 minutes break I am giving here. After this, I will be continuing with the selection of the insulation because it's a short, what we call time span only. 6:30 to 9:30 means it's a 3 hour class. Generally, we don't use to give a break. But listening for 3 hours is a bit difficult only. That's why at 8 a.m. I will give a break of 10 minutes. Okay, fine. So I have resumed audio video on screen. Resumed audio video on screen. Yeah. Kindly at this topic what we are discussing now. That is a selection of insulation level, overhead line insulation level. So to learn about it, first I will be showing one transmission tower, cross arms, insulators, conductors, all these things I will show first in a simple schematic diagram. Consider it was a transmission tower, which we can say as a pylon, or you can say lattice structure, pylon, or you can say it's a lattice structure. So these are cross arms I am showing. Cross arms. Right, corresponding to the phase A, phase B, phase C cross arms. Yeah, look. So this tower is connected to ground like this. Okay, and this is called as cross arm. Cross arm. Next. See, this is a phase A conductor. You can assume conductor A, okay. And it was a conductor B I am showing, and it was a conductor C. Between the conductor and tower, as we said, we have a overhead line insulator. Like this, we have some overhead line. It's a type of string insulator. If you want, you write that name. String insulator. We'll discuss this in the insulators chapter. String insulator. Okay. Next. Yeah. One more suggestion from my side. All of you listen. You can text your doubts in the Telegram also. As a class is going on, some people might be feeling a difficulty to type in Q&A. Okay, you can type your doubt in the Telegram also, right? So if you type in Telegram, the advantage is if I am unable to give answer for you as a live, I can give the answer for your doubt later also. Okay, so I think all of you getting my point. What I said, you can type your doubt in the Telegram. That may be easy to that number what I have given to you. Yeah, let me continue. Listen. See, this is a three-phase transmission line system having voltage level, let us say 132 kV, and power level of 150 MVA. 130 kV, 150 MVA. Can you please tell me what is this 130 kV here? 130 kV. All of you, please tell me what do you mean by 130 kV? It's a line-to-line RMS voltage rating of line. Line-to-line RMS value. And what do you mean by 150 MVA? It's a three-phase apparent power rating. 150 MVA is three-phase apparent power rating. All of you getting this? Okay, now listen. We are concentrating to select the insulation level. Selecting the insulation level means simply how much amount of voltage will appear across the insulator. That we have to check first. For example, let me concentrate on this phase B insulator. It's a phase B insulator. Across this insulator, how much amount of voltage is possible to appear? Okay, that we have to know. Listen, please. Listen. Very simple concept and very familiar concept also. Look here. This tower is connected to ground, na? Tower is connected to ground. What is ground potential? Anybody? Anybody please tell me. What is ground potential? Yeah. 0. Ground potential is 0. See, it is one of the major assumptions in the complete electrical engineering analysis. complete whole electrical engineering analysis, this voltage is assumed as 0 because this ground is a common terminal at all places. At all places. Okay, now I'll tell you this insulator is connected between, look my words. Insulator is connected between conductor and ground. Conductor and ground. So conductor and tower. And the tower is connected to ground. Else I can say conductor is connected to ground. Conductor is connected to ground through two bodies. One is an insulator, next one is a tower. Okay, so tower is made by which material? Tower is made by which material? Galvanized steel. Galvanized steel. What do you mean by galvanization? What do you mean by galvanization? Yeah, adding zinc to the steel in order to avoid the corrosion. Okay, so steel is a good conductor of electricity, definitely. Steel is a good conductor of electricity, and it is having some resistance of something like R tower. That insulator might be having a resistance of R insulation. Insulation might be having a resistance of R insulation. Okay, Vishwanath, you please ask your doubt in the doubt session. Vishwanath, you please ask your doubt in the doubt session, please. Next, let's continue. Now what I can say is conductor B is connected to ground through two resistances. One is a insulation, next one is a tower. But how is a tower resistance value compared to insulation resistance? How is a tower resistance value compared to insulation resistance? It's very, very low or negligibly small. Tower resistance will be negligibly small compared to the insulation resistance. Why it is so? Means tower is a good conductor. Insulator, it's having very high resistance in the order of mega ohms. Now, tell me, in this series connection of R insulation and R tower, can I neglect tower resistance value? I need your response now. In the series combination of R insulation and R tower, can we neglect the tower resistance? Yes or no? Yes, because it's a very, very low number. So you can neglect it. So R tower can be neglected. Now, by neglecting the tower resistance value, can I say this point as ground? Can I say this point as ground? Yes or no? Nobody is saying, nobody is answering. This point itself is going to be called as ground point, which is operating at zero potential. Now, could you please tell me the insulator is connected between what? Insulator was connected between what? Conductor and ground. Insulator was connected between conductor and the ground. Now tell me, what do you mean by conductor to ground voltage? What do you mean by conductor to ground voltage? What do you mean by line to ground voltage? What do you mean by phase to ground voltage? It will be definitely per phase voltage only. Okay, so the voltage across this insulator is a phase voltage, V phase. How much is the value now? How much is the phase voltage value? Line to line value 132. Line to line value 132. Phase voltage, it will be 132 kV by root 3. 132 kV by root 3. Now you please tell me, is it required to design the insulator based on line to line voltage? Is it required to design the insulator based on line to line voltage? Or can we go with only per phase voltage? We can go with only per phase voltage. Per phase voltage is sufficient. You no need to go with the line to line voltage. Okay? Yeah, I'm writing that statement as a conclusion from this whole discussion. So, overhead line insulator need to be designed based on per phase voltage. Based on the per phase voltage. Okay, simple statement. per phase voltage. Yeah, I'll come to that, Ashish. I'll come to that, Ashish. It's not the final statement. It's not the final statement. Still, we have more expansion. Expansion. Yeah. Design. One more thing. Imtiaz. We are discussing this in the designing stage only, not in the operation. Designing stage only we are discussing. Now, next. Listen, please. Listen. For example. Okay. Before going for that example, let me tell you. What is conductor operating voltage B? Anybody tell me, please? What is conductor B operating voltage? See, if anybody asks you this question, simply by showing three lines outside, what is conductor A voltage? What is conductor B voltage? What is conductor C voltage? With respect to what you measure that voltage? With respect to what you measure that voltage? Will you measure that conductor B voltage with respect to the other conductor or with respect to ground? If I am asking you to measure any one conductor voltage, will you measure that with respect to ground or with respect to other conductor? With respect to ground, definitely. Yes or no? So what is this conductor B to ground voltage? Phase voltage only, line to line voltage by √3. And what is conductor A to ground voltage? Means conductor A voltage. That is also phase voltage only. And what is conductor C voltage? That is also phase voltage only. So each and every conductor in this three-phase transmission line operates at a voltage of per phase voltage. So called line to line operating voltage by √3. Line to line operating voltage by √3. All of you getting? Simple thing. Let me go ahead further. Let me move ahead further to the next slide. Okay. Look. Now, so I am taking one specific example here to explain about that voltage, insulation level selection. Look, I am taking one transformer. Star delta. Have a look at this. It's a primary side. Okay. Primary side. And I am showing secondary side delta. Some delta shape like this. Secondary side delta. Yeah. See, from this delta side of the line, from the delta side of transformer, we have three lines going out. We have three lines going. Phase A, phase B, phase C lines going. Something like this. This is a phase A line. And this is a phase B line. And this is a phase C line. Three lines are going out. Okay, next thing. Listen, stop writing. I will give some time to copy. Just listen to my words. It's a bit confusing. Already I discussed. Whoever is attended fault analysis class, I have discussed that, but still I am repeating because it is a bit confusing topic. Look, this transformer is having a rating of 400 kV primary side, 220 kV secondary side. 400 kV primary side, 220 kV secondary side. Simple. What do you mean by this 400 kV? Is it line to line or per phase? Definitely line to line. Yes or no? So 400 kV, whatever they said, that is nothing but line to line terminal voltage of the transformer. Line to line terminal voltage of transformer. Kindly understand my words. Line to line terminal voltage of transformer. Primary side. What is 220 kV? Irrespective of this transformer connection, primary line to line voltage 400 kV. Secondary line to line voltage is 220 kV. Secondary line to line voltage is also equals to 220 kV. All of you getting? Line to line voltage. Next thing. Very simple question. What is conductor A voltage magnitude? What is conductor B voltage magnitude? What is conductor C voltage magnitude? Tell me this. What is conductor A magnitude? Conductor A voltage magnitude? Is it 220 or 220 by root 3? 220 or 220 by root 3? Many of you are giving correct answer. 220 by root 3 kilovolts. What is conductor B voltage? Also 220 kV by root 3. Conductor C also 220 kV by root 3. Okay. 220 kV by root 3 is a phase A, phase B, and phase C voltages. All of you getting me? All of you getting? Okay, but many of you might be having a doubt that, sir, this is delta, this is delta. So as far as delta is concerned, you know phase voltage equals to line to line voltage. In case of delta, phase voltage equals to line to line voltage. I'm not disturbing that statement. What you should say exactly is, listen, all of you, whoever is having a doubt, listen. A delta phase winding voltage, and line to line voltages are equal. That is the meaning. Okay, see, as far as this winding is concerned, this winding voltage will be 220 kV. I am not at all disturbing that. Winding voltage is 220 kV. I am not at all disturbing that. But what I am asking here is, what is this point voltage? What is this point voltage? See, the point voltage, if you want to find the point to what we have to get. This point voltage I am asking now. Point A voltage I am asking now. With respect to what you measure that voltage? With respect to B or with respect to ground? Tell me all of you. Tell me all of you. The point A voltage we should measure with respect to ground, not with respect to conductor B. If you measure with respect to B, you get 220 kV. If you measure with respect to ground, you will get that voltage 220 kV by 3. 220 kV by 3. That is a terminal voltage or conductor operating voltage. Conductor operating voltage. Yeah. Now tell me please, tell me. Irrespective of this transformer connection, what we have, is it a star connection or delta connection? Doesn't matter. Doesn't matter to me. I will feel this transformer simply as a black box. I will feel this transformer simply as a black box. Whatever the outcoming lines we have, and we know line to line voltage, and each conductor will operate at a voltage of line to line voltage by root 3, irrespective of transformer winding connection. Is it a correct statement or not? Is it a correct statement or not? I will come to your doubt, Avinash. Just listen my words. Is it correct statement or not? Yes. So tell me please, while we are selecting the insulation level of the overhead line, is it required to look into the winding? Is it required to look into the winding, what is supplying the power? Not at all needed. Irrespective of the winding connection, always overhead line insulator has to be designed based on per phase voltage only. Okay, so I'm writing that here. This one, irrespective. I'm writing that irrespective of transformer winding connection. Irrespective of transformer winding connection, we have to design the overhead line insulation level only based on the per phase voltage, so-called line to line voltage. Now, obviously, Amrit, correct, Amrit. Okay, let's move ahead. I will ask one very simple question. This may make you very clear. Anil, just listen, Anil, what I am saying you. Listen, it may make you clear. It may satisfy you what I feel for all your questions. Tell me, you have 3 insulators, right? Phase A to tower, phase B to tower, phase C to tower. Total 3 insulators. How these 3 insulators are connected? Anybody? How these 3 insulators are connected? Vishnu Ajit, kindly listen to this one, what I am saying you. How these 3 insulators are connected? Is it in star? Definitely. Yeah, Charan, I have identified it. Please excuse me for this only. Okay, but I don't have a space to write down. That's why I have written. See, this point, this point, this point, all these three will be tower point only, right? And tower is grounded. Tower resistance is assumed as 0. Then obviously, for example, if you take up this conductor A and this is conductor B and this is conductor C, something like this, you take, and A2 tower we have an insulator, C2 tower we have an insulator, B2 tower we have an insulator. And all these insulators are, sorry, all these endpoints are shorted by this tower, are connected by the tower. Maybe like this. It is a tower junction. Okay, ends of the insulators are connected by the tower. And the tower is connected to ground. Na? The tower is connected to ground. Tower is connected to ground. Now you please tell me, you are applying a voltage of 220 kV between this conductor A to conductor B. 220 kV between the conductor A to conductor B. You tell me please, what is conductor A to ground voltage? What is conductor A to ground voltage, and what is conductor B to ground voltage, and what is conductor C to ground voltage? That will be definitely 220 kV by root 3. Shreyas, have you understood this? Shreyas? So I have seen for one crosser, there are 5 lines attached with the ring. Okay, I will come to that, Raviteja. I will come to that. That is a bundle conductor. I will come to that. Yeah. So this conductor A voltage is nothing but 220 kilovolts by root 3. This is a way how we have to understand. This is a way how we have to understand. So I think all of you getting this one clear. Now I think you are clear. Irrespective of this winding connection, your insulators are connected in star, right? Your insulators are connected in star. Definitely, each insulator will experience a voltage of 220 kV by root 3. 220 kV by root 3. Yeah. Next. So I'm moving ahead. Can I move? Can I move ahead? See this? Let me come back to this diagram, what we are discussing. Let me come back to this diagram. See, this insulator has to be designed for a voltage of 132 by root 3 is a comment what we have made. Now the question is like this. If you are designing, listen. If you are designing this insulator, that particular insulator, for a voltage of 132 by root 3, the meaning of that statement is, if the insulator is experiencing a voltage more than this number, if this insulator is experiencing a voltage more than this number, definitely insulator will damage. Correct or not? You are designing this for 132 by root 3, means if the voltage across this one is more than this number, then definitely insulator is going to be damaged. Okay, tell me now, can we have a voltage more than this number? Yeah, yes, Ramakrishna. Can we have a voltage more than this number? Particularly, we are discussing about a sinusoidal signal here. Sinusoidal signal. Just look at this sine wave, what I am plotting. It's a per phase voltage sine wave I am showing. Per phase voltage sine wave, something like this. Per phase voltage sine wave. And what is it 130 kV by root 3? What is that 130 kV by root 3? That is RMS value. Per phase RMS value. Maybe that 132 kV by root 3 may lie at this place. This is a V phase RMS value location you can feel. V phase RMS value location you can feel 130 kV by root 3. Now tell me please, can we have a voltage more than this phase voltage RMS value? Can we have an operating voltage more than this phase voltage RMS value in the sinusoidal wave? Yes, particularly in this portion. In this portion, the voltage is coming more than the RMS voltage. Voltage is coming more than the RMS voltage. So listen. So in this portion, as a voltage is crossing RMS value, there is a possibility for the damage of the insulator if you design it based on RMS value. Repeating the statement, very simple. I designed the insulator based on RMS value. Okay. By looking at the waveform, voltage is coming more than RMS value. Definitely, if the voltage is coming more than RMS, insulator will be damaged. Now, based on what voltage we should design the insulator? Based on what voltage we should design the insulator? Whichever the highest value we are getting, based on that, we should design the insulator. So all of you getting this? Whichever the highest value is nothing but this peak voltage. Based on this peak voltage, we have to design the insulator. Okay, so I am modifying the earlier statement. And I am writing that overhead line insulator design shall be designed based on per phase peak value or peak voltage. Per phase peak voltage means it is nothing but line to line RMS value by √3. It's a per phase RMS into √2. It's a per phase. Based on this voltage, we have to design the insulation. Yeah. 220 kV by √3 multiplied with √2 for 220 kV rated voltage design. Yeah, next thing. Actually, Bhavani, after applying this voltage across the insulator will experience a voltage stress. If the voltage stress, else you can say electric field intensity also. If that value was greater than, listen please. If that value was greater than the dielectric strength of the insulator is going to be damaged. That's the problem what we are discussing now. Okay, so if the applied voltage is more across the insulator, obviously insulator will experience more stress, and if it's higher than its dielectric strength, insulator is going to be damaged. So if we design it based on RMS value, we have a voltage higher than this number. Because of that higher voltage, insulator may damage. So we have to design it based on highest voltage what we are experiencing. So that's why I'm considering that as peak voltage. Yeah, Shahil, you are correct, Shahil. Sir, previously you told for designing lines, we don't consider peak only. RMS, peak, we don't consider. See, actually, anonymous attendee, those are ratings. What I said. Okay, RMS value is the rating. But designing point of view, with what voltage we have to design, that we have to decide. Okay, next, let me continue. So I think all of you clear. Now, next, one more question I am asking. Very simple question again. Just look at this diagram. This voltage 130 kV by √3 into √2. For that voltage, we are designing the insulator. 132 kV by √3 into peak voltage. Based on this voltage, we have designed the insulator. Okay, now listen to my question. After designing the insulator for this much amount of voltage, if the voltage across the insulator is more than this number, then again the insulator is going to be damaged and we can experience a flash over. Tell me, is there any possibility of getting voltage more than this number across the insulator? Is there any possibility of getting voltage across the insulator more than this number under any circumstance, under any situation of operation? Tell me please. Yes, when we are going to get it, particularly during over voltages, surge voltages, during the time during the time, definitely voltage across the insulator comes higher than this value and the insulator is going to be damaged. Okay, now based on what voltages we have to select the insulation level. Is it based on normal steady state operating voltages or over voltages? Based on what value we have to select the insulation? Is it based on rated voltage or over voltage? Is it based on rated voltage or over voltage? Definitely based on the over voltage, we should select the insulator. Okay. See, listen. What we are attempting to do here is, in a single point, I'll tell you. In a single point, I'll tell you what we are attempting. What we are attempting to tell here is simply, after if I keep the insulator on the tower, look, if I keep the insulator on the tower, after that, the insulator should not be damaged at any cost. At any operating condition, my insulator should not be experiencing any flashover, such that we should select the insulation level. Then only we can avoid the flashover. We can avoid the flashover. Getting a flashover is nothing but creating the conductor to ground fault, right? Getting the flashover is nothing but creating the conductor to ground fault. All of you getting my words? What we are attempting to do? We are attempting to avoid the insulation flashover for any operating voltage. Means we are attempting to avoid the occurrence of the line to ground fault under the operating conditions of system. Yeah, I don't know whether you have understood this point or not. All of you clear? If you are clear, I will write that statement. Yeah. So I am writing that statement as a note. Insulator has to be designed in such a way that it should not experience any flashover at any operating condition. Okay, this is a note what you have to do. At any operating condition. Yeah, please go through this, Sangeeta, what I have written. So therefore, generally, overhead line insulation will be designed based on overhead line insulation will be designed based on surge voltages. Surge is nothing but transient. Don't feel that's a new term. It's a transient. It's a synonym for transient. Surge voltages. Okay. So now we'll be continuing with what are the different types of over voltages. What's the different types of over voltages? A flashover and corona is not same, Divya. Flashover and corona is not same. Okay. Flashover is simply after experiencing that high stress of insulator, we get a flash. This is an arc between the conductor to tower via insulator. That we call as flashover. Yeah. So now I'm taking up in the next slide. As a heading like the different types of over voltages. Major over voltages only we are going to discuss. Major over voltages in the system. Look once. Major over voltage in the system. See, we have different types of over voltage, but I am considering only major here. Two. First one is a lightning over voltage or lightning surge, lightning transient, any name. Second one, switching. Switching surge, transient or over voltage. First one, lightning surge, you can say, or lightning transient, you can write, or lightning over voltage. OV, I am writing OV in the sense over voltage. Second one, switching. Switching surge, you can say, switching transient, or you can say switching over voltage. Switching over voltage. Yeah. Lightning and switching. Next thing. First, let's continue. Let's continue with the lightning over voltage first, or lightning surge first. Taking up the first heading here. Lightning. Yeah. Look, what do you mean by lightning? What do you mean by lightning? See, basically, particularly in the rainy season or foul weather conditions, bad weather conditions, you can see some spark in the sky. You can see some spark in the sky. That's what you can say as a light, right? That's what you can say as lightning. Yeah. See, actually, what will happen is, there will be some charges. There will be some charges accumulated in the cloud, maybe because of friction. Because of friction between the water drops and all. We used to have some charges accumulated in the cloud. See, according to weather conditions, what I said is, whatever the charges accumulated or stored in the cloud, might be discharged into other cloud beside that, which we can say cloud to cloud discharge. Next one, the charges stored in the cloud might be discharged to the ground, which we can say cloud to ground discharge. So lightning, in our view, we have two types. One, in the sky, cloud to cloud. Next one, cloud to ground. What we have to concentrate now? Cloud to cloud or cloud to ground? Which one we have to concentrate? Whichever is reaching to earth, that's the thing we have to concentrate. Means we should think about cloud to ground discharge only. Okay, next. Which bodies on the ground will take this lightning? Which bodies on the ground will take this lightning? Means simply conducting bodies. Conducting bodies will attract this lightning. So, in a simple point, what I'm going to tell here is, lightning discharge is a discharge of cloud to the conducting body on the ground. Okay, so I can say here, lightning discharge is a discharge of cloud to the conducting body on ground. So it's a discharge of cloud to the conducting body on the ground. Conducting body of the ground. Okay, next point in the lightning. In what form it will be? Lightning will be in what form? Is it in the form of voltage or current? Tell me please. Lightning discharge, is it in the form of voltage or current? Just observe here clearly. See, you can observe flow of charges. Look here. You can observe flow of charges from cloud to ground, right? From cloud to ground, you can observe flow of charges. Flow of charges means what? It's a current. current. So lightning discharge is basically a current. Basically, it's a current. Okay, next thing. Current, decided. Which form? Which form? Form in the sense, in what waveform? Is it a DC, sinusoidal, or any other waveform? In what waveform you can experience that current? Impulse. Why in the sense? Within a short span of time, maybe in the span of microseconds or milliseconds, huge amount of charge injected onto the conductor. So it will be in the form of impulse. So basically, this lightning discharge, it's a impulse current. Impulse current. So I think all of you getting this point. So it's an impulse current. Impulse current. Lightning discharge, it is in the form of impulse current. Okay, now tell me, else, it's a simple thing to know in a general way. How much is this current value in the sense? It will be in the order of kiloamperes. Impulse current will be in the order of kiloamperes. Generally, it will be in the range of 10 to 100 kiloamperes. 10 to 100 kiloamperes. That's the range of that current. 10 kiloamperes to 100 kiloamperes is a range of that impulse current to be expected. Yeah. Next. In a simple way, this is a way how we have to understand now. Whenever, listen. For example, this is a conducting body. It's a conducting body. Whenever that lightning attacks on the conducting body, definitely the conducting body will carry some current. Lightning current, you can see it's a conductor. It's a lightning stroke. So whenever it is injecting some current, definitely some current will flow in this one. And whenever some current is flowing in the conductor, because of that current, magnetic flux is created. Look, magnetic flux is created, linking with the conductor. Definitely, it will create a voltage on the conductor. Definitely, it will cause for a induced voltage on the conductor. Yes or no? That voltage is very, very large number that we are going to name it as lightning over voltage. Okay, so this impulse current, whatever it is injected onto the conductor, will create a over voltage. Which is going to be called as lightning over voltage. Okay, so if you want to write impulse current or lightning impulse current will create lightning impulse current. Impulse current creates an over voltage. Okay. Now I will try to show that waveform. See, live tree, it's a conductor. Tupati Bhavani, live tree, it's a conductor. Yeah. So let me show that impulse voltage waveform. Just observe. It's a time axis I am showing, and it was a voltage axis. Okay, and it's a time axis. Generally, ideal impulse signal means maybe in control systems or maybe in signals and systems you might have studied. Okay, ideal impulse signal is simply like this now. Ideal impulse signal simply like this, you can see. This is the ideal impulse. But how is a practical impulse signal? Practical impulse signal you don't expect in this manner. The practical impulse waveform might be something like this. Just observe. We have a straight rise, large rise at the beginning, and we have a fall. Sharp rise, better word is sharp rise. Very sharp rise you can experience. It will be almost along with the voltage axis. Just show you. along with the voltage X, something like this. Like this, you can experience. We have a sharp rise in the voltage, but there is a fall. And this fall is a bit, it will take a bit a good amount of time. That fall will take a bit of good amount of time. Like this, you can experience the impulse voltage waveform. And this peak value, I will be denoting this as capital V, capital V. And I'm showing some timings on the x-axis. Yeah, see, Sandeep, life is a conductor, that's for sure. And it may be touching to distribution lines at some places, but it may not be a perfect contact, but still, it's a conductor in the sense it may be having a good amount of resistance, good amount of resistance. That's the thing what you have to understand. Yeah, look here. So I'm showing some timing here. Kindly observe. This is some time TR, and I'm showing one more voltage here, 0.5 times of V, 0.5 times of V, and I'm showing this time as a TF. See, TR is going to be called as rise time and TF is going to be called as fall time. Two times here, one is a rise time, other one is a fall time. TR and TF. Okay. So if I have completed, I will move to next slide to give some description about it. Yeah. See, generally, this impulse over voltage, generally impulse over voltage represented as P by TR by TF. Generally, that impulse over voltage is represented as a terminology like V by TR by TF. V is a peak voltage in kilovolts. It's a peak voltage in terms of kilovolts. TR is a rise time in microseconds. TF is also fall time in microseconds. TF, it's a fall time, that's also in microseconds. That's also in microseconds. V by TR by TF. So you have to get my intention exactly what I'm saying. You have to get my intention exactly what I'm saying. For example, a transient voltage given as represented as transient voltage represented as 1000 by 1 by 50. What do you mean by this? Yes, they will give transient voltage like 1000 by 1 by 50. My intention is to tell you, they don't keep kilovolts and microsecond in this description. They don't give the kilovolts and microsecond in this description. That you have to understand on your own. And you should say peak voltage 1000 kV. 1000 kV. Rise time 1 microsecond. Fall time 50 microseconds. 50 microseconds. Like this you can say. Okay. Done. Next. See, actually, in olden days, maybe in the times of 1930 and 1940s, at the time, majority of the damages to the power system network, majority of the damages to the power system network is coming due to the lightning. Suddenly, a lightning attacked on some transformer, lightning attacked on some transmission line, that is causing a severe damage, maybe a disconnection also, maybe blackout. It may be causing for some sort of blackout in the system. Okay. So at that time, we have IEEE. That IEEE decided to count at least how many number of lightning strokes are reaching to ground from sky. Getting me? Very simple words I am saying. In olden days, we are facing many problems with respect to these lightning strokes. That's why IEEE decided to overcome this issue. In order to overcome this issue, first they want to know how many strokes are experienced by the ground from the sky. And for that, that work was allotted to some IEEE committee. IEEE committee. That committee has done some extensive survey, and finally they submitted a report that number of strokes. Listen. Number of strokes reaching from sky to ground, is in the order of hundreds. 100 strokes in 1 second, or 150 strokes in 1 second. Like that, we are going to experience. See, it is throughout the Earth's surface, I am saying. Throughout the Earth's surface, including the oceans. Okay. And along with that number of strokes, they identified one more term that, or one more point that lightning is going to occur only on the topmost conducting body, on the ground surface. On the ground surface nearby, whichever the topmost conducting body you have, on that one, the lightning stroke is going to occur. That's the point what they have identified. Okay, let me write that point. Lightning generally occurs on topmost conducting body. Topmost conducting body. Lightning generally occurs on topmost conducting body on the ground surface. It's not possible, sir. It's not possible. On ground surface. Ground surface. Yeah, so I think yeah, next. Listen. Now, so that's why you can see if you have a big hotel, hotels are some special places. They used to keep one tower on the top of that building. They used to keep one tower on the top of the building, and they used to keep some sort of conducting body, maybe iron rod or something, and that's going to be grounded in a proper way. So by that way, if there is any lightning to be attacked on the building, that will be attacked on the top conducting body what they kept, and that will be diverted to ground. So it's going to provide some sort of protection. It's going to provide some sort of protection for the building from the lightning strokes. Okay, coming back to the power system network. See, in the power system network, we have some major equipment like generator, transformer, transmission line. These three. Generator, transformer, transmission line. Among these three, which equipment is having more probability to get a stroke? Which equipment is having more probability to get a stroke? Can we please? Which equipment is having more probability to get the stroke? It will be transmission line. Why it is so means it's not because of its height. It's a widespread equipment on the ground surface. So widespread equipment on the ground surface. So I can say transmission line has more probability to get the stroke. Compared to other equipment. See, remaining equipment also, we provide the protection from lightning strokes, definitely. We provide the protection from the lightning strokes, definitely, but we are discussing now with respect to the transmission line. See, for example, if you have a transmission tower, something like this, it's a schematic diagram again, just for the sake of understanding. Okay, so it's a transmission tower, I can say, like this. And power conductors are running on this tower. Maybe it's a phase A conductor, and it's a phase B, and it's a phase C conductor, like this. Power conductors are running on this tower, something like ABC. Power conductors, ABC. Yeah. Next thing. Listen. See, in order to avoid the stroke occurrence on the power lines, simply I will keep some dummy conductor on the top of the tower. Just I will keep one conductor simply like this. Simply we will keep one wire on the top of the tower. Extra wire you feel just be kept on the top of the tower. Now tell me, if there is any lightning stroke released by the cloud, lightning stroke coming from the cloud, is it going to be attacked onto this dummy wire or on the power lines? On what that lightning stroke is going to be attacked? Is it on the dummy wire? Yeah, on the dummy wire, obviously. See, what I can say simply is, whatever the extra wire we kept on the top of the tower, it is going to provide some sort of protection or shielding. Shielding or protection, both are same words. Okay, for the power lines from the lightning strokes. Hence, we are going to call this wire, topmost wire, as a lightning shield wire. Lightning shield wire. Lightning shield wire. Okay, it's not neutral wire. It's not neutral wire. This wire is completely out of our system. Completely out of our system. While you are doing analysis on the power transmission line, maybe steady state analysis while you are doing on the power transmission line, you no need to consider this lightning shield wire. No need to consider the lightning shield wire. So I think most of you might have seen this wire outside. Most of you might have seen this wire outside. Yes or no? Yes. Okay. Tell me now. Tell me some simple properties of this wire. Some simple properties of this wire. How is the size of this wire compared to power line? How is the size of this shield wire compared to power line? Very less. It's a thin wire. Thin wire. Maybe it's a steel. Galvanized steel wire we will use practically. So lightning shield wire, it's a thin wire. Thin wire. And moreover, it is a galvanized steel. Galvanized steel wire. Okay, next. Is there any insulator? Is there any insulator kept in between? Yeah. Is there any insulator kept in between this lightning shield wire and tower? No, it is directly connected to tower. Directly connected to tower. Directly connected to tower. It is directly connected to tower. Okay, next question. See, as a lightning shield wire is directly connected to tower, can I say it is connected to ground directly? As a lightning shield wire is directly connected to tower, can I say it is directly connected to ground? Yes or no? Yes. Yeah, it will be definitely connected to ground directly. So we can call this wire as a ground wire also. Lightning shield wire can also be called as ground wire, or you can say earth wire. Ground or earth wire. These are the other names what you can prefer for this wire what we have shown on the top of the tower. Okay. So this is about lightning over voltage what we are discussing. Just go back. If you have any doubt, just go back and check this one, what I am saying you. We have started our discussion. With what we call selection of insulation level for the overhead lines. First we said simply phase voltage. Per phase voltage. Again I said it's not just per phase voltage. We should take per phase peak value. After that I said generally we experience some over voltage in the system. So we should design it based on the over voltages I said. And in the over voltages, major over voltage will be two. One is lighting, next one is of switching. Now we are discussing about lighting till this point. Now we should think about switching. Okay. So next type of over voltage here is switching over voltage. Next type of over voltage is switching over voltage. See, when these switching over voltages are going to occur, in a simple way, see, switching over voltages are going to occur particularly during switching operations. Maybe opening the breaker, closing the breaker. Opening, closing, both will create the over voltage or some transient in the system. Why the transient is created? After all, our power system network is consisting a large number of inductors and capacitors, storage elements. Okay, so whenever you make a switching operation, definitely there is a certain change required in the storage of the inductor and the capacitor. Because of that, definitely there is a transient created, and that will be leading to the over voltage in the system. Okay, so switching over voltage occurs during switching operations. Occurs during switching operations. Switching operations. Okay. See, in a simple thought, who are doing these switching operations? We as operator, we as operator, engineer, we are making those switching operations, right? Can I say these over voltages are internally created over voltages? Can we say these over voltages are internally created over voltages? Yes or no? Yes. So switching over voltage can also be called as internal over voltage in the system. These are internal over voltages in the system. Internal over voltages in the system. But what about lightning? What about lightning? It is coming from. It's coming from what? Other space. It's coming from space, means other body. From external, we are getting the over voltage. So lightning over voltage can also be called as external over voltage. Lightning over voltage can be called as external over voltage. I'll write it someplace. Yeah, I'll write here only. Lightning can be called as external. And switching can be called as internal. Switching can be called as internal. Okay, next. Next thing, look here. Next thing. See, are you capable to avoid? Listen to my question and answer. Are you capable to avoid the occurrence of lightning over voltage in the system? Means on the transmission lines. On the transmission lines, I am saying, are you capable to avoid? Are you capable to avoid lightning over voltage in the system? Yes or no? Yes, by keeping that ground wire on the top of the tower. By keeping the ground wire on the top of the tower, we are capable to avoid the attack of the lightning stroke onto the power conductors, right? So if at all any lightning we have, that will be attacked onto this ground wire only. It may not directly attacking on the power transmission lines. Okay, tell me. Are you capable to avoid the occurrence of switching over voltage in the system? Are you capable to avoid the occurrence of switching over voltage in the system? Yes or no? No, we can't avoid it. Because we can't avoid the internal switching operations in the power system network. Maybe for a load disconnection, load addition, line removal, we have to do these internal switching operations for a regular maintenance. Regular maintenance. So switching over voltages we can't avoid. So I can say switching over voltages are unavoidable. Switching over voltages are unavoidable. The system. Switching over voltages are unavoidable in the system. Now, almost we reached to the end of this topic. Almost we have reached to end of this topic. Now the question what I am asking is, based on what over voltage we have to select the insulation level? Based on what over voltage we have to select the insulation level? Is it based on lightning or switching? Is it based on lightning or switching? If anybody asks you this type of question, what you have to answer is, listen please, what you have to answer is, whichever is higher among these two, based on that, we have to select the insulation level. Okay, let me write the point in a note. Overhead line insulator, overhead line insulation level has to be selected based on based on highest among lightning and switching over voltages. Switching over voltages. Lightning and switching over voltages. Okay. Yeah, Jessica, these are internally created, right? These are internally created. Somebody is having a doubt again. Sir, already you said in the previous discussion, you said that lightning can be avoided by keeping ground wire. Lightning can be avoided by keeping the ground wire. Then again, why you are calling that lightning in this discussion? Already you are avoiding lightning, right? So you can go directly with the switching. Is it a doubt? Is it a doubt? Yes or no? Yes, definitely. So just listen what I'm going to tell you here. Just listen. For example, look once. Stop writing, just listen. For example, some lightning was attacked onto this ground wire. On the ground wire, lightning was attacked. After that lightning was attacked, whatever the current injected, current will divide into two parts, and that current will flow in this ground wire definitely. Repeating the statement, just listen concentratedly. Very simple network theory concept. Lightning attacked on the ground wire. Lightning attacked on the ground wire. Current divided into two parts. One part is flowing like this, other part is flowing like this. Means simply what I can say is ground wire is carrying some very large amount of current. Ground wire is carrying very large amount of current. Because of this current, it will produce a magnetic flux. Am I correct or not? Am I correct or not? It will be producing some magnetic flux. That magnetic flux will be linking with the power lines. That magnetic flux will be definitely linking with the power lines. Because of that linkage, a large amount of EMF is going to be induced in the power lines. Is it a over voltage? Is it a over voltage? I am not getting any response. Not getting any response. Is it a over voltage? Yes. It's a over voltage. Okay. Next. Is it due to lightning? Whether this over voltage is due to lightning or not? This E over voltage, is it due to lightning or not? Yes. But is it a direct attack or indirect? Is it a direct or indirect? Indirect. Rani, indirect. Direct means what? Direct means if the lightning is directly attacked on the power line, that's a direct voltage. But if the lightning attacked on some other body, creating a over voltage in the power conductor, it is called as indirect. Following all of you. So we have two types of lightning over voltage now. Two types of lightning. One, direct lightning over voltages. Second one, indirect lightning over voltages. I think all of you getting my point. Is it okay? Is it okay? Yes. Okay. Now tell me. I am asking one simple question. Direct lightning over voltage. Are you capable to avoid this on the power conductor? Direct lightning over voltage. Are you capable to avoid it on the power conductor? Yes. By keeping ground wire. Sivateja. Listen. Direct lightning over voltage we are capable to avoid by keeping the ground wire. Are you capable to avoid the indirect lightning over voltage? No, we can't avoid the indirect lightning over voltage. Can we avoid the switching over voltage? No, we can't avoid the switching over voltage. So we have to design the overhead line insulation highest among indirect lightning over voltage and switching over voltage in the system. Indirect lightning over voltage and switching over voltage in the system. That's the reason why we have to consider the lightning over voltages also in the insulation level selection. You get it? Here. Lightning falls on tower, there is no issue. It's an indirect only, right? Anonymous attendee. Lightning falls on the tower, it's an indirect stroke only. It's not coming directly onto the power conductor. It may be discharged to ground. May be discharged to the ground. See, whenever that lightning current is flowing something like this, some part of that is going to be discharged into ground like this. Remaining part will flow. Remaining part will flow. Okay, whatever the remaining part we have, that will reach to the next tower, and some part is diverted to ground by a tower, and remaining part will flow. Again, some portion will be diverted to tower, and remaining. Like that, successively, tower by tower, this lightning is going to be, lightning discharge will be diverted to the ground continuously. Okay. So let me continue. Now. See, particularly for listen, for voltage levels, operating voltage levels greater than or equal to 300 kV line to line. 300 kV line to line. Switching over voltage magnitude will be greater compared to the lightning over voltage magnitude. Switching over voltage magnitude will be greater compared to lightning over voltage magnitude. Okay, this is observation from practice. This is observation from the practice. Generally, for operating voltages greater than or equals to 300 kV line to line, switching over voltage will be greater compared to lightning over voltage. Now, above 300 kV, what are the voltage levels we have in India? Above 300 kV, what are the voltage levels we have in India? 400 kV and 765 kV. Yes or no? 400 kV and 765 kV. For those levels, so-called for 400 kV and 765 kV levels, if they have asked you to select the insulation level, based on what over voltage we have to select? If they have asked you to select the insulation level, based on what over voltage you have to select, that will be based on the internal over voltage, or you can say switching over voltage. Okay, so I'm writing the statement. Therefore, for 400 kV and 765 kV lines, 765 kV lines, insulation level shall be designed based on, or shall be selected also, you can say, based on switching over voltage or internal over voltage. Why this so means? Simple reason is switching over voltage will dominate the lightning over voltage, and we have to select one among these two, whichever is higher. That's why I am selecting the switching over voltage for this. Ajay, Earth is a neutral body. Ajay, Earth is a neutral body. Even you keep some charges into the Earth, it will take. Even you want to supply, it will supply. That's the meaning. Neutral body. Earth is a neutral body. So lightning discharge will go into Earth. It will be absorbed by ground. That's it. Yeah, 760 kV we have in India, many places. Okay, now I'm asking one silly question, simple question also, of course. Don't confuse. Just listen my words. I want to give some clarity. To you. Just listen. 11 kV line. 11 kV or 33 kV line. What you see just outside. 11 kV or 33 kV. Based on what over voltage we select the insulation. Is it lightning or switching? 11 kV line. Based on what over voltage, we have to select the insulation. Is it lightning or switching? See, actually, listen. While you are considering this lightning over voltage into the analysis, height is a matter. Height of the tower, height of the line is definitely, it's a prominent one. If the height of the line or height of the tower is very high, if the height of the line or height of the tower is very high, then only we have to consider the lightning over voltage in the calculation. Else, it is not required to consider. Will you accept it or not? Yeah. While you are considering that, when we have to consider the lightning, when we have to consider the lightning over voltage. Yeah. Whenever the height of the tower or height of the line is very high, height of the tower or height of the line is very high, then only we have to consider the lightning. Height, how much height in the sense that depends upon the other objects beside that system. Okay. So, particularly if you think about 11 kV, 33, 66, maybe of 130 kV, tower height may not be too high. Tower height may not be too high. If that is the case, it may not be required to consider the lightning over voltages in their insulation level selection. In their insulation level selection, it may not be required to consider the lightning over voltages. Maybe at a level of 220 kV, there is an ambiguity. Which voltage we have to consider? Is it lightning or switching? But as a simple conclusion, listen please. As a simple conclusion, what I am going to tell here is simply, most of the times, insulation level will be selected based on internal over voltage only. Lightning over voltages will be considered very rarely. Very rarely. All of you getting my words? Yeah. We are going for 400 kV lines and 75 kV lines. Height is very high. There I have to consider lightning. That's okay. There I have to consider the lightning. That's okay. But switching is dominating lightning. So for 400 kV and 75 kV, I have to go with switching. But remaining lines, if I take these lines, height is less. Right? It is not having a good probability of getting lightning. So we no need to go for lightning over voltage there. We can go with switching only. Getting me? So generally, as a note I am saying, generally, insulation level of any line will be done based on, or will be selected based on, switching over voltages. So if you want, you write that other statement also here. Lightning over voltages will be considered. Lightning over voltages will be taken into analysis. If tower height is very high. Okay. That's the other point what you have to remember. Yeah. So we stop at this point today. As it's the first class. Tomorrow we'll be going with the classification of voltage levels in the system, like 11 kV, 33. These voltage levels I will discuss. So after that, we go with the different types of conductors to be used in the power transmission system. So class was completed at this point. If you want, you can leave, and if you have any doubt, you can stay. Daily we have a class starting from 6:30 a.m. to 9:30 a.m. Daily we have this class. Particularly on Sundays. On Sundays, you have a class from 6:30 to 1. On Sundays, you have a class from 6:30 to 1. Okay, tomorrow, the timing is this one. But tomorrow, this is the time, 6:30 a.m. to 9:30 a.m. If anybody have daily same timings, every day 3 hours only. May not be 3 also. Some days, I may leave you early also. 8:30, 9 o'clock also, I will leave some days. Okay, don't take too much stress. Just read the thing, whatever I have discussed, whatever I am discussing in the class daily. Okay, so no tiffin break in between. I will give only 10 minutes break. I will give only 10 minutes break. There is no tiffin break. Yeah. So if anybody having doubt, you please raise your hands. I'm making all the hands low. I made all the hands low. You can raise your hands. Samad, Abdul Samad. Samad.
Good morning, sir. Hello. Hello.
Tell me Samad.
Am I?
One minute. Sir, in schedule it is showing 4.5 hours daily. So actually, Avinash, there will be a what we call doubt session, right? That's why they might have given 4.5 hours. We have a class of 3 hours daily. Okay, 3 or less than 3 little sometimes. Sometimes if I have taken less than 3, I may go up to 10 also some days. Okay. The subject is easy only. Yeah, please go ahead, Samad.
Audible, sir. Audible.
Yeah, audible. Tell me.
Sir, in selection of overhead line insulation level, sir, phase voltage is 132 by root 3. Sir, why multiply by root 2?
Peak value we have to get, right?
Okay.
That's what I have shown here. Peak voltage will be line to line voltage by root 3 into root 2.
Okay.
That's a peak. If you want, you write here V phase maximum equals to root 2 into V phase RMS, right? From basic sinusoidal signal. Getting?
Thank you. Yeah, sir.
That's it?
That's it.
Okay, fine.
Thank you, sir.
Gurudatta.
Yes, sir.
Gurudatta.
Good morning, sir.
Tell me, Gurudatta.
Good morning, sir.
Good morning.
Sir, that impulse voltage representation, please explain that once.
Which one you want?
Impulse voltage representation.
This one?
Yes, sir. Yes, sir. Previously.
Okay. What do you want here?
Sir, what is the meaning of B? TF, sir.
What is it? TR and TF.
Yes, sir. Yes.
TR is the rise time.
Okay, rise time and fall time.
Yeah, that's it.
Okay, yes, sir.
Any other doubt you have?
No, sir.
Okay. Can I mute you?
Yes, sir.
Bhavani.
Good morning, sir.
Good morning, Bhavani.
Sir, as you said, for less than 300 volts transmissions lines, height takku untadi, lightning raadu annaru kada sir.
No, lightning possibility is very less, I am saying.
Sir, akkada manam insulators ni based on switching toni design chesthe okkasari lightning occur aithe it will damage na sir.
Yes, definitely it will damage. But in that view, we can't spend that much capital, right? For example, Bhavani.
Yes, sir.
Bhavani.
Yes, sir.
If you want to design all the insulators based on lightning over voltage.
Okay.
Even for 11 kV line also, you have to keep this big size of insulator.
Okay.
Understanding the problem what I am saying?
Yes, sir.
So obviously, your line looks to be very bulk.
కానీ అక్కడ డిస్ట్రిబ్యూషన్ లైన్ మొత్తం పాడైతది కదా సార్ ఇప్పుడు మనకు ఇన్సులేట్
see again as a backup protection we used to keep lightning arresters, surge arresters at regular intervals.
Yes.
Okay, that will divert the surge, right? It may not transfer to the distribution line.
ఓకే సార్. సార్
Tell me.
అనదర్ క్వశ్చన్.
Tell me.
ఓకే సార్, క్లియర్. సార్ ఇప్పుడు మీరు క్లాస్ చెప్తున్నారు కదా, ఈఎస్సి అండ్ గేట్ 2 కవర్ చేస్తున్నారా సార్?
Whatever the 8 topics I have shown there, it will be for both ESE and GATE.
సార్ మీరు ఈ స్పెసిఫై చేస్తారా సార్, ఈ సిలబస్ గేట్ కానీ ఈ సిలబస్ ఈఎస్సికి వస్తుందని?
అమ్మా సబ్జెక్ట్ ఒకటే ఏ ఎగ్జామ్ కైనా. ఓకేనా?
డెప్త్ వేరే ఉన్నాయి కదా సార్, డెప్త్
రెండు ఒకటే.
విషయంలో వేరే.
రెండు ఒకటే ఉంటుందమ్మా, డెప్త్ ఏం పెద్ద డిఫరెన్స్ ఏమి ఉండదు. మీకు గేట్ కోచింగ్ తీసుకున్నా ఈఎస్సి క్వశ్చన్స్ డిస్కస్ చేస్తారు, ఈఎస్సి కోచింగ్ తీసుకున్నా గేట్ క్వశ్చన్స్ డిస్కస్ చేస్తారు, అవునా కదా? ఓకేనా? సో సమ్ అడిషనల్ టాపిక్స్ ఆర్ దేర్ ఫర్ ఈఎస్సి దట్ ఐ విల్ డిస్కస్ లేటర్.
ఓకే సార్.
Okay, so whatever I am discussing now, it is for combined GATE as well as ESE, both.
ఓకే సార్.
Okay.
దట్స్ ఇట్ సార్. థ్యాంక్ యూ సో మచ్.
Yeah. Tulsi. 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 Udviraj.
Hello, sir.
Tell me.
Sir, what is indirect lightning, sir?
For example, you have lightning stroke on what we call ground wire.
Okay, sir.
So ground wire is carrying current,
Okay, sir.
creating magnetic flux.
Okay, sir.
That flux is linking with the power line.
Okay, sir. Okay, sir.
That is creating an EMF in the power line.
Okay, it is inducing voltage in power.
Induced
line.
over
Okay, sir.
voltage. Induced over
Okay,
voltage. It's a indirectly created lightning over voltage.
Okay, sir.
Okay.
Sir, one more doubt I am getting is when you are taking a ground wire, if lightning strike at that ground wire, it will have current in both the directions. Am I right, sir?
Yes, correct.
Then EMF may be induced in opposite polarities in the power conductor that may get cancelled like that. That effect will not occur.
One thing, insulator is experiencing what voltage? Conductor to ground or end voltage?
Which one, sir? Insulator, sir?
Insulator.
It's a conductor to ground, sir.
Then what's the problem of summing up? Sudhi?
Sir?
What is the problem of, what is the issue of summing up voltage?
Sir, no, I'm asking in this way means
Very
current
simple,
is
Sudhi.
flowing. Sir.
It is a power conductor. Okay.
Okay, sir.
Lightning stroke. You are
Okay,
asking
sir.
me, this is some current I by 2, sir, and this is some I by 2.
Yes, sir.
And this is creating an EMF in this direction, E.
Yes, sir.
Better I will show this. E. And you are saying this, sir, like this.
Yes, sir.
Insulator is
Sir, I'm
experiencing
ask-
this voltage only, right?
I am asking in case of indirect lightning case, not direct lightning
Even
case.
in indirect lightning case also, half of the line may experience some voltage, remaining half will experience a different voltage.
Okay, sir. Okay. Means in terms of flux, it is showing +5, that is showing -5.
Very, very simple, very simple. Where you are connecting the insulator.
Insulator with respect to ground and power conductor.
That's it. So that voltage only you should think. You should not sum up this voltage, right? This voltage you no need to take, right?
Okay, sir.
Half of the conductor is experiencing some voltage. Remaining half is experiencing some voltage. You are saying some of these two is 0, sir. So insulator will not will experience 0. Is it so?
Sir.
But where you are connecting insulator, along the power conductor or conductor to ground.
Conductor to ground, sir.
This is the insulator portion, right?
Yes, sir. Yes, sir.
This will experience voltage, but this whole voltage is 0.
Okay, sir.
Chance is there, okay?
Okay, sir.
Yeah.
So
Any other doubt
we
here?
are
Tell me.
sir. We are considering lightning over voltages for the voltages like 132 kV and 220 kV only.
Some cases, some special cases only we will consider that lightning. Unless otherwise it will be switching mode.
Switching over voltages.
Yeah.
Okay.
Okay.
Thank you.
Is Akshay. Akshay.
Good morning, sir. Am I audible?
Yeah. Tell me, Akshay.
Sir, one doubt I had was direct lighting over voltage. When we say that, it means that the lightning directly strikes the power lines, right?
Power line. Yes, correct.
And that is avoided using the earth wire or ground wire.
Yeah, correct.
Correct. Okay, sir. Clear, sir. Sir, then
Mhm.
one more thing. I am from the OPM 6 new batch. So, did we have any power system topics covered before? And
No,
will
no need to worry. That will be covered again for you. Okay.
Okay, sir. Can I like will that matter for the
No,
remaining?
nothing.
Oh,
Whichever
okay,
is
sir.
required, we will discuss in each and every topic separately. We don't link up this topic to the other. For example, even that link will be there definitely, what I am saying to you. But if there is that type of link, that specific point we'll discuss and we'll move.
Okay, sir. Okay,
Okay.
sir. Thank you, sir. Okay.
Yashwant.
Sir, my doubt is when you considered the selection of OH line insulation level, you mentioned about the transformer connection type, slide number 15.
Okay.
Yeah, 18.
Tell me.
I did not understand the per phase voltage concept here because delta anyways line voltage is equals to phase voltage.
No. In delta, line to line voltage equals to phase winding voltage.
Okay. Phase
Okay.
voltage is directly, the terminals are directly taken out as a line.
Okay, I am asking you this terminal voltage. What is that voltage? Yashwant.
220.
Why 220? How you say? See, to measure the voltage, we need to have two terminals, right? Between what terminals you are saying this voltage is 220?
Between terminal A and terminal B.
That's line to line then. It's not terminal A voltage.
Suppose we take.
If you are measuring A to B voltage, it will come line to line. It's not conductor voltage of A.
Okay. The winding voltage itself is taken as terminal voltage, or is it not taken?
No, that's wrong. No.
Okay.
Terminal voltage is terminal to ground.
Okay.
Winding voltage means line to line voltage.
Okay.
Very simple thing, Yashwant. Remember always, if anybody asks you what is a particular conductor voltage, you should say that voltage from that conductor to ground. That's it. Understanding, Yashwant?
Okay. Yes, sir.
Okay.
So 220 kV by root 3 becomes our per phase voltage.
Per phase voltage of transmission line, you say, if you are confusing.
Oh, per phase voltage of transmission. Yes, this is clear. This is clear. Good. Thank you.
Naveen Sai.
Sir, good morning, sir.
Good morning.
In the causes of switching over voltages, we have opening and closing of circuit breaker, no, sir.
Yeah.
While opening of circuit breaker, that means you are disconnecting a line, a feeder or something.
Okay.
So for that reason, we may have over voltage. But when we close the circuit breaker, we are loading it. So no, sir. So how over voltage occurs, sir? There will be drop in voltage, no, sir.
Hey, Naveen.
Sir.
Whether you are opening the breaker or closing the breaker,
okay,
whatever it is, you are disturbing the position of inductor and capacitor charging.
Yes, sir.
Whenever you are disturbing the position, charging position of inductor and capacitor, definitely there will be a transient creation.
Okay.
Definitely it may lead to a over voltage sometime.
I'm getting confusion
you may be
in this.
In an impression that, sorry, if you disconnect the load, so current flow is less, voltage is high.
Yes.
because
Yes, sir.
drop is less. That's a steady state concept, right?
Okay, sir.
But in the transient period, whenever we are disconnecting the circuit or connecting the circuit, whatever it is, definitely
Okay.
there is a change in the current flow as well as a voltage across these natural elements of inductors and the capacitors. Because of that, definite transient is going to be created.
Okay, sir. I
Okay,
mean,
I will ask one very simple question to you. Naveen.
Sir.
I have one DC voltage source here
Okay.
connected to resistor and an inductor. Okay.
Yes,
Whenever the
sir.
switch is getting closed, at the instant of the switch closing, what's the inductor voltage?
It is a total voltage. It appears. Total voltage appears.
Total voltage it will appear. But according
Yes,
to
sir.
your view, it should be less, right?
Okay. Okay.
Cannot
Okay, sir.
happen.
Understood now, sir.
We are discussing in transient period. Yes or no?
Yes, sir. Okay.
Mhm.
Now I got it. And one more doubt, sir. This transformer configurations from generation to distribution. What is that configuration, sir? I mean,
I'll discuss
star
that in
delta.
creator and distributor tomorrow.
Okay, sir. Okay.
Tomorrow I'll discuss about it. Which type
Okay,
of connection we are going to use for step up, step down, as well as in distribution system.
Okay, sir.
Okay. Tomorrow
Thank
we'll
you, sir.
discuss. Yeah.
Okay, sir.
Gautami.
Hello, sir. Good morning, sir.
Good morning, Gautami. Tell me.
Sir, in 17F, sir.
Okay.
Sir, line to line voltage already we are considering RMS values, sir.
On the nameplate or rating, it will be RMS only, Gautami.
Okay, sir. Sir.
For example, if somebody says that this is a line rated for 400 kV.
Okay, sir.
By blind mark, you should say it's a 400 kV line to line RMS.
Okay, sir.
Because that is the standard what they will represent. Okay.
Okay, sir. Then again, when we are calculating with respect to ground, we are taking phase one, sir.
Per phase voltage.
Okay, sir. Sir, then again another question is, sir, when lightning stroke is attacked to conductor, that's the flow of means
current.
Yes, sir, current. So that's why then conductor will damage them, sir.
Which conductor?
Means over current means first of all current will damage, then after going to insulator. Means what
Gautami,
yes, sir.
Your point is that if there is a overcurrent, the conductor will damage.
Yes, sir.
Then you have to think about insulator and all. That's the point what you're saying. Yes, sir?
Yes, sir. Yes, sir.
Okay. Why conductor will damage if there's a overcurrent?
Means over electrons means if more electrons.
You don't go micro level electrons than all. Huh? You tell me as a basic way, go to me. Very simple point I am asking you.
Yes, sir.
Many people will say, and many textbooks also will say that if there is a overcurrent flow in the conductor will damage.
Yes, sir.
I am asking you why. Why it will damage?
Why means resistance value 0.
Resistance value
current.
not 0.
Okay, sir. Means
tell me whatever the thing you have in your mind. That's correct. Tell me, please.
Yes, sir. I mean, 4 voltage means insulator damage. If over current means.
That's okay. Over current means conductor damage only. Why?
Yes.
Why?
Yes, that I don't know.
Because of heat.
Okay. Yeah.
Heat.
Yes. Okay.
What's the heat formula?
I square into
I square into R into
T.
Time.
Yes,
what is the time? For how much amount of time this current is passing through the conductor?
0, within less.
Not 0. For example, if you consider the lightning, it will be in the order of 50 microseconds. Yes or no? What is that overall period I have given here? 50 microseconds. It's in the order of microseconds what I am saying.
Yes, sir.
So if you take this time in the order of microsecond, what is the overall heat developed because of that large current flow?
Very less.
Very less. So
Yes,
that
sir. Yes, sir.
conductor damage may not happen during this transient
Okay, sir.
because transient timings are very, very small.
Yes, sir.
The transient times are very small. Heat developed is very less.
Okay, sir.
So chances of having the conductor melting, conductor damage is very less. But within a short amount of time, there is a possibility for the damage of the insulator because of the overstress.
Okay, sir.
That's why during surge timings or transients and all, the people will discuss about the damage of the insulator only rather than the conductor damage.
Okay, sir.
Understanding?
Yes, sir. I understand, sir.
Oh, right.
Yes, sir. Clear, sir.
Any other
Okay.
doubt you have?
No, sir. That's all. Okay. Thank you, sir.
Imtiaz.
Good morning, sir.
Morning, tell me.
Sir, in the selection of the voltage rating of the insulator, we are using the root 2 into VRMS the root 3, no, sir. Sir, it's a design purpose or also at the operating purpose?
Design.
Means,
Actually, listen. Actually, the 220 kV is a rated voltage.
yes, sir.
220 by root 3 is a rated per phase RMS.
Yes, sir.
Into root 2 is a rated per phase peak.
Yes, sir.
After coming into operation, if the operating voltage is 210 kV, operating voltage 210 kV, okay?
Yes, sir.
In line to line RMS.
Yes, sir.
Then what is the operating per phase voltage? 210 by root 3.
Yes, sir.
Operating per phase peak voltage 210 by root 3 into root 3.
Yes, sir.
That's it.
But if the I confuse in that in we study in the fault analysis, no, sir. If the ground is not there, then the phase voltage will become the line voltage, no, sir.
Operating voltage. Operating voltage.
That's operating voltage.
Operating. Not rated voltage, right? Getting me?
Sir,
Imtiaz.
it's confused. One second.
Simple. We have 3 lines. Rated voltage is 220 kV, line to line, RMS. Okay?
Okay, sir.
Line to line RMS. And for example, if you have some fault on some of the conductors, this voltage is coming 0.
Yes, sir.
Okay? And this voltage is coming some other value.
Yes,
and
sir.
this is some other voltage you are getting. Okay?
Yes, sir.
What is this V? So for example, this VB is coming to me something like RMS value only 220 kV. And this VC also coming like 220 kV too. What is 220 kV, 220 kV? Rated voltage or operating voltage?
Operated. Rated, sir. Sorry.
Operating.
Yes, sir. It's
Rated
working.
voltage of conductor is 220 by root 3, right?
Yes, sir.
Operating voltage is coming to 20 kV.
Yes, sir.
You are designing the insulation based on rated voltages.
Yes, sir.
But operating voltage is coming higher than the rated voltage.
Yes, sir.
Because of that, there may be a possibility of flashover.
Yes, sir.
Okay, tell me what's your doubt?
Actually, dot means if the ground is ungrounded, at that time phase voltage become the line voltage. No, sir. We study in the fault
Operating
analysis.
voltage. Phase voltage of the operating phase operating voltage of the conductor equals to line operating voltage.
Oh, yeah, it's confusing operating, and I understand, sir.
Clear now?
Yes, sir. Sir, one more, sir. Sir, in the surge impedance of the lighting arrestor, we are using the thin wire of the galvanized steel, no, sir.
Okay.
Sir, it can be withstand for the 100 kilo amps. That the
How much
thin
is the
wire.
time?
It's in microseconds.
That's what I explained just now. Heat.
Okay, sir.
It's very, very low, right?
Yes, sir.
Then obviously, even though you have a thin wire, a high resistance wire, it makes no difference to me.
Okay, sir.
Because
Sir,
heat development is very, very less.
Yes, sir. Sir, one more, sir. Sir, aluminum conductor used for the less density and less cost is the advantage, no, sir? Hello? Hello, sir. Hello. Sir.
Yeah, Imtiaz, are you there?
Hi, yes, sir.
Yeah, please go ahead.
Sir, in copper, in aluminum, we have the advantage of the less density and less cost, no, sir.
Yeah.
Sir, why we are not using it the home purpose? We are using the copper in small machines and home. Could you tell?
Actually, direct load is connected nearby this what we call distribution. Sorry, this house wires.
Direct load means?
Direct load means you have light, fan, and all, right?
Hi, yes, sir.
So if you are using aluminum wire, there voltage drop may be more.
Okay. Main reason is the voltage drop.
1 minute, please. 1 minute.
Okay, sir.
We have a call from our academy. Imtiaz, go ahead. Imtiaz.
Sir. The main reason for the not selecting the aluminum in the house purpose means the voltage drop.
Voltage drop is the main purpose. One more thing, Imtiaz. Investment view also you can say. For example, if you are using aluminum wires, life of aluminum wire will be a bit less compared to copper.
Okay, sir.
Okay, that's one thing. And size of aluminum conductor will be bigger.
Hi, sir.
Conduit size means PVC pipe what we are going to lay in the wall.
Yes, sir.
That pipe size also requires larger.
Yes, sir.
Okay. Some issues are there. That's why we prefer to go for copper inside our house.
Okay, sir. Sir, could you tell I did not understand the voltage drop and power losses, the relation between the voltage drop and power losses. You asked that doubt.
I don't say a relation between them. Those two are separate words.
Yes, sir. When the voltage drop occurs, the VR will be less than the VS, no, sir.
Yes, correct.
Why means? Could you tell that, sir? Means you said one relation, sir, at that time.
KVL application.
Yes, sir.
Sending an voltage minus voltage drop equals to receiving an voltage.
Yes, sir. Power losses is and voltage drop, there is some relation, no, sir.
There is no relation between power loss and voltage drop, Imtiaz.
Okay, sir. Means you said, no, not mathematical relation, sir. You said in class, but at that time my network.
No, those two I have discussed separately. Even though I have discussed that under the same heading of desirable characteristics, but those two are separate words.
Okay, sir.
Okay, power loss is more, I have to reduce it.
Yes, sir.
If voltage drop is more, voltage drop also I have to reduce.
Both are different.
Different
okay, aspects. Sir. Okay, sir. That's all right. Thank you, sir.
Avinash.
Hello, sir.
Tell me, Avinash.
Sir, in a rise time and fall time graph, sir, please.
1 minute, Avinash, 1 minute. Yeah, this is the last doubt I am going to take up. There is another class at 10 o'clock. That's why I'm closing this session quickly. Tomorrow onwards, we will see some alternative. We'll see some alternative. Doubt session will be continued till the end of the last doubt, definitely from tomorrow. For this day, please excuse us. If you have any doubt, you can ask me in Telegram. You can ask me in Telegram. Okay?
Okay, sir.
Yeah. Tell me out quickly.
Sir, in a rise time, fall time graph, sir, sir, the time duration of the fall time is much greater than rise time as compared to the rise.
Correct. Yes.
Sir,
That's a practical observation only. Avinash.
Yes, sir.
It's a practical observation only to say fall time is very, very large compared to rise time.
Okay, sir. Sir, means some valid reason means you can give in short.
No, actually, if you try to take up this ideal impulse signal, means practical impulse signal.
Okay, sir.
Okay, so it will be having in this nature only. There's no practical reason for it. Sorry, mathematical reason for it. Practically observed impulse waveform they have given.
Okay, sir. And sir, one more doubt is there. Sir, you have told the ground wire, the neutral wire is very thin.
Not neutral wire, ground wire.
Sorry, sir, ground wire. Ground wire is very thin. So, sir, how it can be sustained the large amount of current of light?
Why can't it flow that much amount of current? Why can't we have that much amount of current flow in the thin wire? What's the problem?
Sir, the magnitude of the current is too much high. That's why, sir, and in a thin wire, so the cross section area is very, very less.
What will happen? What will happen?
So, sir, how means it could flow? So,
see, actually, because sir, heat is a reason. Heat is a reason for the damage of the conductor.
Yes, sir.
But for how much amount of time that current is flowing?
For microsecond.
So I square into R into time is a heat.
Yes, sir.
Time is very less, no?
Yes, sir.
So heat development is very less. So conductor will not damage.
Okay, sir.
Understood,
Yes,
Avinash?
Thank you, sir.
Okay, fine. So any other doubt, you can ask me in Telegram or we will continue tomorrow doubt session. No issue. Okay. Thank you. I am closing the session. Thank you.